How long is a day on Mercury really? There are places in our solar system where the familiar rhythm of a day breaks down entirely. Places where you could watch the sun begin its slow climb, only to see it pause in the sky, drift backward, and then continue on its way. A world where a single day, from one sunrise to the next, lasts longer than its own year. In fact, it lasts for two of them. This is not a world from fiction. It is the real, quietly strange reality of the first planet from our Sun. This is a day on Mercury. The planet challenges our most basic understanding of time itself, reminding us that normal was never the plan. So what would it be like to stand on its surface and watch this cosmic ballet unfold? Let's explore this mystery, one slow, strange rotation at a time. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. If this kind of calm exploration into our solar system helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a quiet town, or somewhere in between, feel free to share where you're watching or listening from. Anchoring ourselves to Earth. Before we journey to the sun-scorched surface of Mercury, it helps to look again at a word we think we know: day. Here on Earth, the concept feels intuitive. We think of the 24-hour cycle of light and darkness, the time it takes for the sun to appear in the same position in the sky, from one noon to the next. Astronomers call this a solar day. It is the day of our clocks and our lives. But there is another kind of day, one that is more purely astronomical. It is called the sidereal day. This is the time it takes for the Earth to complete one full 360-degree rotation on its axis, measured against the distant, so-called fixed stars. If you were to pick a star far out in the cosmos and align it with a landmark, a sidereal day is the time it takes for Earth to spin once and bring that star back into alignment. That time is 23 hours, 56 minutes, and 4 seconds. The reason for this 4-minute difference is subtle, but it lies in a second motion we are all familiar with: our orbit around the Sun. As the Earth spins, it is also moving through space on its year-long journey. Each day, it travels a considerable distance along its orbital path. So, after it completes one full rotation relative to the stars, it has also moved. Because of this, it needs to rotate just a little bit more, about 4 minutes worth, for the sun to appear back in the same position. It has to catch up. This 4-minute gap may feel like a small piece of trivia. For all practical purposes on Earth, our solar day is the one that matters. It governs our seasons and the rhythm of life. But this quiet distinction, this dance between rotation and orbit, is the absolute key to understanding why Mercury is so profoundly strange. On Earth, the two types of days are nearly the same. On Mercury, the difference between them is so extreme, it creates a world that would feel utterly alien. This small gap on Earth becomes a chasm on Mercury, responsible for all of its temporal weirdness. Understanding this dual nature of a day is our first step off our home world and onto the strange, dusty plains of the first planet. The journey to Mercury and the central problem. Now, let's leave the familiar comfort of our earthly clockwork behind. Our destination is a world of extremes. Mercury, the smallest planet in our solar system, and the one that orbits closest to the Sun. This proximity dictates everything about it. From Earth, it is often lost in the glare of sunrise or sunset. But to truly understand it, we must imagine ourselves on its cratered, rocky surface. The first thing you would notice is the sky. The sun would appear more than twice as large as it does from Earth, hanging in an inky blackness. But it is not just its size that is different, it is the pace of its journey. And this is where we encounter the central, mind-bending problem of Mercury. The numbers tell a story that defies intuition. First, Mercury's year. Because it is so close to the Sun, it completes one full orbit in just about 88 Earth days. It is the fastest planet, a true cosmic speedster. Now, let's look at its rotation. This is where things get strange. Mercury is a slow spinner. For it to complete one 360-degree rotation on its axis, its sidereal day, it takes about 59 Earth days. While Earth spins once in under 24 hours, Mercury takes nearly 2 months to do the same. Standing on its surface, the stars would crawl across the sky at an almost imperceptible rate. So we have a very fast year and a very slow spin. But here is the detail that seems to break logic. If you were to ask how long a solar day is on Mercury, the time from one sunrise to the next, the answer is not 59 days. The answer is approximately 176 Earth days. A single day on Mercury is 176 Earth days long. Its year is 88 Earth days long. This means a single Mercurian day is twice as long as a Mercurian year. You would experience 2 full years in the time it takes for a single day to pass. You would celebrate a birthday and then another one, all before the sun that rose on the first day had even set. This is where our Earth-bound intuition begins to fail. How can a day be longer than a year? The numbers seem to contradict one another, presenting a riddle written in gravity and light. But it is not magic, it is physics. It is the result of a quiet, precise, and gravitationally enforced dance between the planet and its star. To understand it, we must dive deeper into the mechanics of this strange world. The explanation: unraveling the cosmic mystery. The answer to Mercury's temporal puzzle lies in a concept known as a spin-orbit resonance. Specifically, Mercury is in what astronomers call a 3:2 spin-orbit resonance. This is the secret ingredient. It means that for every 2 times Mercury orbits the Sun, it rotates on its axis exactly 3 times. This is not a coincidence. It is a state of gravitational equilibrium the planet has settled into over billions of years. The Sun's gravity has sculpted Mercury's rotation, slowing it down and locking it into this rhythmic pattern, much like how Earth's gravity has tidally locked our Moon, forcing it to show us only one face. But how does this 3:2 resonance create a day that is 2 years long? To grasp this, we need to look at the movements separately, and then let them converge. First, let's focus only on the rotation. Imagine Mercury floating in empty space. It completes one full 360-degree turn in about 59 Earth days. This is its sidereal day. 3 of these rotations take place over 176 Earth days. Now, let's add the second motion, the orbit. While it is slowly spinning, Mercury is also racing around the Sun in its 88-day year. 2 of these orbits also take place over 176 Earth days. This 176-day period is the time frame where the resonance cycle completes. Every 176 Earth days, Mercury has completed exactly 3 rotations and exactly 2 orbits, returning to the same rotational and orbital position relative to the Sun. Now, let's place ourselves on the surface. Let's start at sunrise. At this moment, a specific spot on Mercury is just beginning to see the Sun. The planet now starts to both spin and orbit. After 59 days, Mercury has completed one full rotation on its axis. But the Sun has not returned to the same spot. Not even close. While it was rotating, it also traveled a huge distance in its orbit. In fact, after one rotation, it has completed 2/3 of its journey around the Sun. To bring the Sun back to the same spot, the planet's surface must play a long game of catch-up. Think of it like this. Imagine you are on a large, slowly rotating platform. This is you on Mercury's surface. Your friend, the Sun, is standing outside the platform. If the platform just spins, you face your friend once per rotation. But now, imagine the entire platform is also being carried on a track that circles your friend. This is Mercury's orbit. After your platform has made one full spin, The entire apparatus has moved. To face your friend again, the platform has to keep turning for a significant amount of time. On Mercury, this additional time is immense. The math of this celestial motion works out perfectly so that exactly 176 Earth days must pass for the Sun to appear in the same position. Let's follow the cycle. Day 0. The Sun is rising. After 88 Earth days, Mercury has completed 1 orbit and 1.5 rotations. The spot that was at sunrise is now at sunset, facing directly away from the Sun. The first year is over, and we have only had half a day, an 88-day period of continuous daylight. After another 88 Earth days, 176 total, Mercury has completed a second orbit and another 1.5 rotations, 3 total. The spot that was at sunrise, then sunset, has now come all the way back around to face the Sun again. And there it is. One solar day has taken 176 Earth days, and in that time, 2 years have passed. The paradox is solved not by magic, but by the gravitational harmony of the 3-to-2 spin-orbit resonance. It is a beautiful, if bewildering, piece of celestial mechanics, a testament to how gravity can shape time in the most unexpected ways. The bizarre implications, experiencing a Mercurian day. Understanding the mechanics is one thing, but what would it feel like to experience this? If we could stand on Mercury's surface, what would we see? The consequences of this resonance create some of the most surreal phenomena in the solar system. We are standing on a vast, cratered plain. On the horizon, the Sun begins to rise. But this is not a swift, steady sunrise. This is a slow, languid affair. The Sun, enormous in the black sky, crawls upward with agonizing slowness. For weeks, it climbs, its searing light bathing the landscape. The ground heats up relentlessly, reaching temperatures hot enough to melt lead. We are now approaching a special point in Mercury's orbit, perihelion, where it is closest to the Sun. As it gets closer, its orbital speed increases dramatically. For a brief period, something incredible happens. Its speed orbiting the Sun temporarily becomes faster than its speed of rotation. From our perspective, the westward motion of the Sun across the sky comes to a halt. For about an Earth day, the Sun hangs motionless. Then, as the orbital speed continues to dominate, the Sun begins to move backward. It drifts back toward the east, toward the horizon from which it just rose. This is known as apparent retrograde motion. From certain longitudes, the effect is at its most dramatic. You could watch the Sun rise partially, stop, dip back below the horizon, and then rise again from the same spot, the famous double sunrise of Mercury. On other parts of the planet, the Sun would trace a small loop in the sky. Time itself seems to stutter and reverse. After this bizarre solar dance, Mercury moves on, and its orbital speed slows. The Sun resumes its slow, westward journey. Finally, after 88 Earth days have passed since the initial sunrise, the Sun touches the western horizon. A Mercurian year is over. The day is only half done. Now, the long night begins. As the last sliver of the Sun disappears, the temperature plummets. With almost no atmosphere to trap heat, the surface radiates its energy into space. The temperature drops from over 400 degrees Celsius to nearly 200 degrees below zero. For the next 88 Earth days, this is your reality. An impossibly long, dark, and frigid night. The only light comes from the stars, brilliant and unwavering in the airless sky. But they move with that same maddeningly slow pace. You would watch constellations that we see rise and set in a single night take weeks to traverse the sky. It is a stillness and a silence that is absolute. During this long night, another Mercurian year passes. You celebrate your second birthday of this day. Then, finally, after 176 long Earth days, a faint glow appears on the horizon. A new day is about to begin. You have survived 1 day and 2 years on Mercury. Grand summary and the bigger picture. So, the mystery of how a day on Mercury can be longer than its year is not a paradox, but a beautiful piece of celestial mechanics. It begins with our definition of a day, and the realization that on Mercury, the rotational day and the solar day are worlds apart. The planet's slow 59-day spin combines with its swift 88-day orbit, all held in place by a 3:2 spin-orbit resonance. This precise ratio means that for the Sun to return to the same point in the sky, a staggering 176 Earth days must pass. The consequences are as fascinating as the cause. This slow dance leads to bizarre phenomena, like the Sun moving backward in the sky. It creates a world of unimaginable extremes. An 88-day stretch of continuous, blistering daylight, followed by an 88-day stretch of deep freeze darkness. It is a world that forces us to abandon our earthly intuition about the flow of time. Mercury is not just a hot rock, it is a dynamic world that still holds secrets. Our quest to understand it is ongoing. The joint European and Japanese mission, Bepi Colombo, is currently making its way to Mercury. When it arrives, it will perform the most comprehensive study of the planet ever undertaken, helping us answer lingering questions about its formation, its large iron core, and the materials that persist on its surface. Ultimately, the strange day of Mercury teaches us a profound lesson. It reminds us that our experience on Earth is just one possibility. The laws of physics are the same everywhere, but the conditions they operate under can create worlds that are wildly, beautifully different from our own. Each planet is a unique laboratory with its own clock and its own story. Mercury's story is one of a slow dance with its star, a story of fire and ice, of time stretched to its limits. It reminds us that there are still so many wonders left to discover, right here in our own solar system. The simple question, how long is a day, turns out to have one of the most complex and fascinating answers when we look at Mercury. It is a world that operates on a timescale so alien it feels like a dream. But it's real, and it's a part of our cosmic neighborhood. If this journey to the strange temporal landscape of Mercury sparked your curiosity, consider exploring some of our other deep dives into the mysteries of our solar system. And if you haven't already, subscribe to the channel to join us on our next expedition. Mercury's day lasts longer than its year. On Earth, there is a rhythm we take for granted. The planet spins, giving us the familiar cycle of day and night. It orbits the Sun, giving us our year. The day is a small part of the year, a predictable and reliable pattern that has shaped all life. We assume this is how planets work. We assume it is the rule. But near the center of our solar system, there is a world that follows a different rhythm. A small, dense planet moving in a quiet, unusual dance with our star. This is a place where a single day, from one sunrise to the next, lasts longer than its entire year. In fact, one of its days is equal to 2 of its years. If you could stand on its surface, you would see the Sun behave in a way that seems to defy simple sense. You would watch it rise, seem to pause in the sky, move backward for a time, and then continue its journey. This isn't a strange fiction. It is the quiet reality of Mercury. The answer to how this is possible is found not in a simple spin, but in a stable gravitational relationship, a cosmic resonance that creates one of the most unusual day-night cycles in our solar system. This is the story of a 3:2 spin-orbit resonance, and how it makes Mercury a planet where our familiar sense of time unwinds. The cosmic anomaly. To understand Mercury's unusual timing, we first had to understand the world itself. It is the smallest of the 8 planets, a ball of metal and rock barely larger than our moon. Its mass is only about 5.5% of Earth's, but its density is nearly the same, which points to the enormous iron core that makes up most of its interior. Its most defining feature, however, is its closeness to the Sun. As the innermost planet, it orbits at an average distance of just 58 million kilometers, or 36 million miles. From its surface, the Sun would appear almost 3 times larger in the sky. This proximity shapes everything about Mercury. It is a world exposed, weathered by a constant stream of solar wind and radiation. Unlike Earth, which is wrapped in a thick atmosphere, Mercury is almost entirely bare. It has what is called an exosphere, a veil of atoms so thin it's almost a vacuum. This is not an atmosphere in a way we would recognize. It cannot hold in heat, and it offers no meaningful protection from space. The result of this is a world of extreme temperatures. During its long day, the surface can reach 430 degrees Celsius, or 800 degrees Fahrenheit, hot enough to melt lead. But without an atmosphere to trap that warmth, as soon as a location rotates into darkness, the heat radiates away into space. During the equally long night, temperatures fall to a quiet, cold -180 degrees Celsius, or -290 degrees Fahrenheit. It is a world of fire and ice, existing at the same time. In fact, one of the most interesting discoveries on Mercury is the evidence of water ice. It survives in the permanent shadows of craters near the planet's poles, in places the Sun's light has never touched. The joint European and Japanese Bepi-Colombo mission is currently on its way to unravel more of these secrets, scheduled to enter orbit in late 2025. These missions build on the work of spacecraft like Messenger, which gave us our first complete map of this quiet world. But its size, its heat, and its ice are all connected to its motion. It moves around the Sun very quickly, completing one full orbit, one Mercurian year, in about 88 Earth days. It is the fastest of all the planets, named for the swift messenger of the gods. So we have a world that completes a year every 88 days. It would seem natural to assume its day must be much shorter. For a long time, astronomers believed just that. They thought Mercury was tidally locked to the Sun in a 1-to-1 resonance, the same way our Moon is locked to Earth. This would mean it rotated once for every orbit, keeping one side in permanent daylight and the other in permanent night. It seemed a simple, logical idea. And it was incorrect. The truth, as is often the case, was something quieter and more interesting. Redefining a day. The central idea, that a day on Mercury is longer than its year, requires us to ask a basic question. What is a day? On Earth, the answer seems simple because two different kinds of day are nearly the same length. On Mercury, they are very different, and this difference is the key. There are 3 units of time to consider: the year, the sidereal day, and the solar day. First, the year. A year is the time it takes for a planet to complete one orbit around its star. For Earth, this is about 365 days. For Mercury, it's a brief 88 Earth days. Next is the sidereal day. Sidereal comes from the Latin word for star. A sidereal day is the time it takes for a planet to make one complete 360-degree rotation on its axis, relative to the distant stars. For Earth, this takes 23 hours and 56 minutes. For Mercury, one full rotation, its sidereal day, takes 58.65 Earth days, or just under 59 days. Already, something unusual appears. Mercury's year is 88 Earth days, and a single spin takes just under 59 Earth days. You might notice that 59 is very close to 2/3 of 88. This is not a coincidence. It is the most important clue. The final piece is the solar day. This is the day we experience in our own lives. It's the time it takes for the Sun to return to the same position in the sky, for instance, from one sunrise to the next. On Earth, this is our 24-hour day. It's about 4 minutes longer than our sidereal day because as the Earth spins, it also moves along in its orbit. It has to turn just a little bit extra to catch up, so the Sun appears in the same place. On Mercury, this little bit extra is stretched into something remarkable. Because its rotation is so slow and its orbit is so fast, the relationship between the two becomes very different. Over the course of 88 Earth days, Mercury completes one full year. In that same time, it has rotated on its axis exactly 1.5 times. If you were standing on the surface at sunrise, after one full year has passed, the sun would not be rising again. It would be high in the sky, or perhaps just starting to set. The planet has not spun enough for the sun to finish its journey. So, how long does it take for the sun to return to the same spot? A single solar day on Mercury, one full cycle from sunrise to sunrise, lasts for 176 Earth days. Let's place the numbers together. A Mercurian year is 88 Earth days. A Mercurian sidereal day, one rotation, is about 59 Earth days. A Mercurian solar day, sunrise to sunrise, is 176 Earth days. And there, the paradox resolves itself. A single solar day, at 176 Earth days, is exactly twice as long as a Mercurian year of 88 Earth days. You would experience 2 full years on Mercury in the time it takes for one day to pass. This timing is not random. It is the result of a precise and stable gravitational phenomenon. The heart of the mystery, the 3:2 spin-orbit resonance. The unusual arithmetic of Mercury's calendar, where 2 years equal 1 day, is the result of a 3:2 spin-orbit resonance. This means that for every 2 orbits Mercury completes around the Sun, it rotates on its axis exactly 3 times. 2 years, 3 spins. This is the quiet rhythm of Mercury. A spin-orbit resonance is a gravitational relationship. The most familiar example is our Moon, which is in a 1-to-1 spin-orbit resonance with Earth. It rotates once for every 1 orbit it makes, which is why we always see the same face. Over deep time, Earth's gravity slowed the Moon's rotation until it settled into this stable state. For many years, astronomers assumed Mercury must be in a similar 1-to-1 lock with the Sun. The Sun's gravity is immense, and Mercury is very close. It seemed logical that the Sun would have forced Mercury to show it only one face. Early observations seemed to support this. When astronomers managed to get a clear look at Mercury, they often saw the same surface features, which reinforced the idea of an 88-day rotation matching the 88-day year. But this idea was corrected in 1965. Using the Arecibo radio telescope, astronomers sent radar signals to Mercury. By studying the Doppler shift in the returning signal, they could measure the planet's rotation speed directly. The result was unexpected. Mercury was not rotating every 88 days. It was rotating once every 59 days. This discovery was puzzling. A 59-day rotation seemed arbitrary and unstable. It was an Italian scientist, Giuseppe Bepi Colombo, who realized that 59 days was not random at all. It was almost exactly 2/3 of Mercury's 88-day year. He proposed that Mercury was in a 3:2 resonance. For every 2 times Mercury orbits the Sun, 2 times 88 equals 176 days. It rotates on its axis exactly 3 times. 3 by 59 approximately equals 176 days. The numbers matched. Let's follow this quiet dance. Imagine a single point on Mercury's surface. Start. The point is directly facing the Sun. It is noon. 1 year later, 88 days. Mercury has completed one full orbit. In that time, it has rotated 1.5 times. Our point on the surface is now facing directly away from the Sun. It has gone from noon to midnight in a single year. 2 years later, 176 days. 2 full Mercurian years have passed. The planet has completed its 3rd full rotation. Because the 2 years and 3 rotations have aligned perfectly, our point is once again facing the Sun. It is noon again. One solar day, the time from noon to noon, has taken 176 Earth days, which is exactly 2 Mercurian years. This 3:2 lock is a stable, repeating pattern. But it brings up a deeper question. Why this particular rhythm? Why not the simpler one-to-one lock? The answer is found in the shape of Mercury's journey. The elliptical dance. The reason for the 3-to-2 rhythm. A one-to-one tidal lock is the most common result for a planet on a nearly circular path. The gravitational pull is relatively constant, allowing a steady slowing of the rotation until it matches the orbit. But Mercury's orbit is not circular. Of all the planets, Mercury's orbit is the most eccentric, or oval-shaped. This means its distance from the Sun changes significantly. At its farthest point, it is about 70 million kilometers, 43 million miles, from the Sun. But at its closest point, perihelion, it swings into just 46 million kilometers, 29 million miles. This changing distance affects Mercury's orbital speed. As it falls toward the Sun, it moves much faster. As it climbs away, it slows down. Now, add the Sun's gravity. Gravity creates tidal forces that try to lock a planet's spin. This force isn't just a simple pull, it's a tidal torque. Because Mercury is not a perfect sphere, the Sun's gravity gently pulls on its slight bulges, trying to align them. The strength of this torque depends on distance. When Mercury is far away, the Sun's grip is weaker. But when it swings in close during perihelion, the tidal forces become much stronger. This is the most important moment in the dance. If Mercury's orbit were circular, the Sun's steady braking would have likely slowed it to a one-to-one lock. But because of the elliptical orbit, the strongest gravitational nudge happened only once per orbit, during the high-speed pass at perihelion. This periodic, strong pull favored a different kind of stability. The 3-to-2 resonance is a state where Mercury's long axis is aligned with the Sun during this moment of strongest gravitational pull, which helps lock it into this specific rhythm. The tidal forces at perihelion are so influential that they stabilize this rotational speed, preventing it from slowing down further into a one-to-one lock. The planet's spin and its eccentric orbit settled into a harmonic balance. So, the elliptical orbit is the cause, and the 3-to-2 resonance is the effect. But what does this look like from the surface? This is where orbital mechanics becomes a quiet, surreal spectacle. A day in the life. The bizarre consequences on the surface. Standing on the surface of Mercury would be an experience completely unfamiliar to our sense of time. The 3-to-2 resonance, combined with the changing speed of its orbit, produces a phenomenon known as apparent retrograde motion of the Sun. Let's imagine you are waiting for sunrise. After weeks in the cold darkness, the Sun begins to appear. But this is not a familiar sunrise. The Sun, already appearing very large, climbs slowly. Then, something strange happens. It seems to slow down, and then it stops. For a time, it hangs motionless in the sky. And then, it begins to move backward, dipping back toward the horizon it just came from. After this brief retreat, it pauses again before continuing its slow, forward journey across the sky. This is sometimes called the Joshua effect, and on Mercury, it is a predictable, physical reality. This solar motion is a direct result of the balance between Mercury's rotation and its orbital speed. As Mercury gets closer to the Sun, its orbital velocity increases. For a short time, the speed at which the planet is moving through space actually becomes faster than the speed of its surface rotation. From your perspective on the ground, the orbital motion is winning against the spin. This is what causes the Sun to appear to move backward. Once Mercury passes its closest point and starts to slow down, its rotational speed once again becomes dominant, and the Sun continues its normal journey. At certain longitudes, you could see a double sunrise. The Sun would partially rise, dip back below the horizon, and then rise again. At other locations, you could watch the sunset, only to see it reappear for a short time before setting for good. One of the most remarkable places to imagine this is at the edge of the Calauries Basin, a huge impact crater over 1,550 kilometers, 960 miles, across. Imagine standing on the mountains ringing the basin. As the sun rises, it would cast long shadows across the floor. You would watch the sun perform its backward loop, and the shadows would shorten, then lengthen again, before finally shrinking as the sun climbs toward noon. And that noon would last a very long time. There are hot poles on Mercury, places that face the sun during its closest, hottest approach. These spots receive an extra dose of radiation, making them some of the hottest places in the solar system. The spot where you are standing could remain under the intense sun for months, before it finally begins to set, signaling the start of the equally long and cold night. This is the lived experience of the 3:2 resonance. It is not just an abstract ratio. It is a physical reality that creates a rhythm of light and heat, of sunrises that pause and noons that last for years. From misunderstanding to messenger, the history of unlocking Mercury's secret. Our understanding of Mercury's day is a quiet story of scientific progress. For a long time, Mercury was just a point of light, difficult to see in the sun's glare. The first major, and famously incorrect, idea came in the 1880s from the Italian astronomer Giovanni Schiaparelli. Observing Mercury was a great challenge, but over years of careful work, he sketched the faint markings he could see. He noticed that the markings often seemed to be in the same place. He concluded, logically, that Mercury must be in a 1-to-1 tidal lock, rotating once every 88 days. This idea was accepted for over 70 years. The irony is that Schiaparelli was a brilliant observer, but he was being tricked by the very resonance he was trying to understand. Because of the 3:2 resonance, Mercury happens to show almost the same face toward Earth during the best times for viewing. He was seeing a real pattern, but he misinterpreted its frequency. This slow correction tells an important story, not just about Mercury, but about how science works. Early astronomers did not fail by getting it wrong. They worked with incomplete evidence and revised their ideas as new data appeared. The paradigm shifted in 1965 with the Arecibo Observatory. Astronomers Gordon Pettengill and Rolf Dice performed the first radar observations of Mercury. The data was clear. Mercury was spinning not every 88 days, but once every 59 days. The 70-year-old consensus was broken. As we've seen, this puzzling number led Giuseppe Colombo to propose the 3:2 resonance theory, a quiet insight that perfectly explained the data. Confirmation came with space exploration. NASA's Mariner 10 flew by Mercury in the 1970s and provided data consistent with the 3:2 lock. But it was NASA's Messenger mission, which orbited Mercury from 2011 to 2015, that truly transformed our view. Messenger mapped the entire planet, confirmed its internal structure, and allowed scientists to create detailed models of the 3:2 resonance. It gave us our first detailed look at the ice in the shadowed craters and the vast Calores Basin. Today, the ESA, JAXA Bepi Colombo mission is on its way to build on that legacy. It is a reminder that even the worlds we think we understand still hold quiet mysteries. The journey from Schiaparelli's patient eye to the instruments of Bepi Colombo is an illustration of how science moves forward, a quiet dance between observation and theory. The story of Mercury is a reminder that the universe is not required to follow our common sense. Unraveling these quiet mysteries is one of the great adventures of science. If this kind of calm exploration helps you unwind, consider liking the video and subscribing to the channel. And feel free to share in the comments what other planetary story you would like to explore next. So, we return to where we began, with a small, scorched world that breaks a familiar rule. A day that lasts for 2 years. This is not a mistake. It is a perfect, stable harmony, the result of a small planet, a large star, an elliptical orbit, and a gravitational conversation that settled on a quiet, complex rhythm. The 3:2 spin-orbit resonance of Mercury is a piece of celestial clockwork. It means that for every 3 times the planet spins, it completes 2 journeys around the Sun. This precise ratio creates everything that makes Mercury feel so unfamiliar. It creates the 176-day solar day, a day so long it contains 2 years. It orchestrates the motion of the Sun, which appears to stop and reverse in the sky. It leads to the extreme shifts from molten heat to quiet cold. Mercury teaches us that time can be relative in a tangible, mechanical way. The simple ideas of a day and a year can be separated, stretched, and woven into patterns we would never expect. The next time you watch a sunrise, remember the small planet close to our Sun. Remember the world where you would have to wait 176 days for that same event, and in doing so, you would have already celebrated your new year. Twice. Mercury, the planet where a day lasts 2 years. The concepts of a day and a year seem fundamental. A day is one rotation of our planet. A year is one trip around our Sun. This rhythm is baked into the fabric of life on Earth. But this is not a universal rule. The universe does not always play by our conventions. On Mercury, the innermost planet of our solar system, these concepts become something else entirely. There, the most startling fact is this. A full day-night cycle takes 176 Earth days to complete. A year on Mercury, the time it takes to make one full orbit around the Sun, is only about 88 Earth days. The conclusion, then, is inescapable. A single solar day on Mercury is twice as long as its entire year. To understand how this can be, we must journey to this world, a place far more alien than its neighborly status suggests. We must set aside our Earth-bound assumptions and learn to think in the language of orbital mechanics. This is the story of Mercury and the quiet physics that shape its strange sense of time. Before we can decode the strange dance of Mercury's days and years, we must first understand the planet itself. It is the smallest of the 8 planets, a tiny, dense ball of rock and iron only slightly larger than Earth's moon. It circles our star at an average distance of just 58 million kilometers, making it the Sun's closest companion. This proximity dictates its speed. It is the fastest planet in our solar system, whipping around the Sun to complete a full orbit, a Mercurian year, in just under 88 Earth days. But being this close to the Sun has created a world of unimaginable extremes. Because it has almost no atmosphere to trap heat or distribute it, the side facing the Sun is baked to 430 degrees Celsius. On the night side, with no blanket of air to retain warmth, temperatures fall to a mind-numbing -180 degrees Celsius. This gives Mercury the most extreme temperature swing of any planet in the solar system. However, the key to understanding Mercury's bizarre day isn't just its closeness to the Sun. It's the shape of its journey. Unlike Earth's nearly circular path, Mercury's orbit is highly eccentric, a stretched-out oval. Its distance from the Sun varies dramatically. According to the laws of planetary motion, a planet moves fastest when it is closest to its star and slowest when it is farthest away. This fluctuating speed is one of the 2 main characters in our story. The other character is Mercury's rotation. For decades, astronomers believed that Mercury was tidally locked with the Sun, meaning it spun on its axis exactly once for every orbit it completed. This would be a 1-to-1 spin-orbit resonance, similar to how our Moon is tidally locked to Earth. The theory was elegant, and from Earth, observational evidence seemed to support it. In 1965, however, that theory was revised. Using the Arecibo radio telescope, astronomers bounced radar signals off the planet's surface. By analyzing the returning signals, they could measure its rotation speed with new accuracy. The result was a surprise. Mercury was not tidally locked. It was spinning, but incredibly slowly. They discovered its rotation period was not 88 days, but rather about 59 Earth days. The old, simple picture of Mercury was wrong, and in its place was a far stranger reality. So we have our 2 key numbers. a year that lasts 88 Earth days and a rotation that takes 59 Earth days. These numbers are connected by a hidden symmetry. 59 is almost exactly 2/3 of 88. This is not a coincidence. Mercury is locked in what is known as a 3-to-2 spin orbit resonance. This means that for every 2 times it completes an orbit around the Sun, it rotates on its axis exactly 3 times. This is the central secret to Mercury's strange timekeeping. It's a stable, repeating pattern. The reason for this strange 3-to-2 ratio, rather than the more intuitive 1-to-1 lock, lies in that eccentric, oval-shaped orbit. The Sun exerts a tidal force on Mercury, creating slight bulges on the planet. The Sun's gravity then tugs on these bulges, trying to slow the planet's rotation. For a planet in a circular orbit, this would eventually lead to a 1-to-1 tidal lock. But Mercury's orbit isn't circular. Because its orbit is so eccentric, the Sun's gravitational tug is much stronger at its closest approach, or perihelion. This periodic, extra tug, is what allowed the planet to settle into a different kind of stability. The 3-to-2 resonance is a celestial compromise, a unique solution to a unique orbital problem. Now we have all the pieces to solve the puzzle of the 176-day solar day. But to do that, we must be clear about 2 different kinds of day. There is the sidereal day asterisk, which is the time it takes for a planet to complete one full 360-degree rotation. For Mercury, this is 58.65 Earth days. Then there is the solar day asterisk, which is the time it takes for the Sun to return to the same position in the sky. On Earth, the difference is minor. On Mercury, it is everything. Imagine standing on Mercury. After 58.65 Earth days, one sidereal day has passed. But in those 59 days, Mercury has moved 2/3 of the way around its 88-day orbit. The Sun is nowhere near where it was in the sky at the start. It turns out the planet has to keep rotating for a very long time to bring the Sun back to its starting position. After a second rotation, it is sunrise. After a third rotation, at 176 days, Mercury has completed exactly 2 full orbits around the Sun. And only now, after 3 full rotations and 2 full years, is the Sun finally back where it started. One solar day on Mercury is 176 Earth days long. Understanding the numbers behind the 3-to-2 resonance is one thing. But these numbers create a solar spectacle unlike anything else in the solar system. This phenomenon occurs around the time Mercury passes through perihelion, its closest and fastest point in orbit. For a brief period, the speed at which Mercury is moving along its orbital path becomes faster than the speed of its axial rotation. For an observer on the ground, the effect is stunning. The Sun, which had been slowly moving westward, appears to slow to a halt. Then, it reverses direction, moving backward, eastward, for a short while. After Mercury passes perihelion and its orbital velocity decreases, the Sun halts its backward motion and resumes its slow journey toward the west. This is a celestial illusion, but one grounded in the reality of orbital physics. This long, bizarre solar day is directly responsible for Mercury's extreme surface temperatures. One side of the planet is exposed to the unfiltered radiation of the Sun for 88 straight Earth days at a time. Then, as the planet turns, that same surface is plunged into an equally long night. The more we learn about Mercury, the more it reveals itself as a world of stunning contradictions. It is the closest planet to the Sun, a place we would assume to be nothing more than a burnt rock. And yet, Mercury harbors ice. This discovery, confirmed by NASA's Messenger spacecraft, is a consequence of the planet's unique orientation. It has an axial tilt of almost 0. This means the floors of deep craters near the planet's poles are in a state of permanent shadow, regions that have not seen a single ray of sunlight in billions of years. In these craters, the temperature is always incredibly cold, a perfect trap for water ice delivered by comets and asteroids. The contradictions continue deep inside the planet. Mercury is the second densest planet in the solar system, which tells us it must have a massive, iron-rich core. In fact, its core is enormous, making up about 80% of the planet's radius. Scientists are still debating why this is. One theory suggests a massive impact in the distant past blew away much of the planet's original rocky mantle. Another posits that the intense radiation from the young sun simply vaporized its outer layers. Even more surprisingly, this massive core is at least partially molten. The churning of this liquid iron generates a global magnetic field, something that, apart from Earth, no other rocky planet in our solar system possesses. The discovery was a surprise, as a small planet like Mercury was expected to have cooled and solidified billions of years ago. From its impossibly long day that lasts 2 of its years, to the bizarre spectacle of its backward-moving sun, Mercury is a testament to the elegant and often counterintuitive laws of physics. It's a world that defies our Earth-centric expectations at every turn. This tiny, dense world of fire and ice reminds us that the universe is not obligated to conform to our common sense. A day isn't always shorter than a year. The closest planet to the Sun can still hide frozen water in its shadows. Mercury is a planet of extremes and a profound lesson in celestial mechanics, a reminder that even in our own solar system, there are mysteries waiting to be unraveled. Mercury's wild orbit makes the Sun go backwards. There are worlds in our solar system that do not operate by familiar rules. Places where the rhythm of a day is so different from our own, it stretches the idea of what a day can be. On the planet Mercury, the Sun does something that seems to violate the fundamental order of the sky. It rises, climbs, and then for a time, appears to stop. After hanging motionless, it begins to move backward, reversing its own path before resuming its forward journey. This is not an illusion. It is a predictable event, born from the planet's unusual relationship with its star. The way Mercury moves through space is so fast, and its path so uneven, that from its surface, the sky itself appears to follow a different set of laws. To understand how this is possible, we need to set aside our Earth-centric ideas of time and look at the two quiet, fundamental pieces that define Mercury's existence: its concept of a day, and its elongated orbit around the Sun. The paradox of a Mercurian day. On Earth, the concept of a day is straightforward. The planet rotates on its axis once every 24 hours, giving us our cycle of day and night. We call this a solar day. There is also the sidereal day, the time it takes to rotate 360 degrees relative to distant stars, which is about 4 minutes shorter. That small difference is caused by Earth's simultaneous movement along its orbit. The planet has to rotate just a little extra each day to bring the Sun back to the same position in the sky. For us, it is a minor detail. But on Mercury, this relationship is the foundation of the planet's strange character. First, there is Mercury's year. It is the fastest planet in our solar system, completing a full orbit in just under 88 Earth days. For a long time, astronomers believed Mercury was tidally locked to the Sun, meaning the same side would always face it, much like our Moon does with Earth. It seemed a logical conclusion. A small planet so close to a massive star would likely be held in a stable 1-to-1 resonance. Early maps of Mercury were even drawn with this idea in mind. But in 1965, our understanding changed. Using the Arecibo radio telescope, astronomers bounced radar signals off Mercury and discovered something unexpected. The planet was not locked in a 1-to-1 ratio. It was spinning, but with an unusual slowness. They found it completes one full rotation on its axis, a sidereal day, every 58.6 Earth days. This revealed a quiet, stable relationship known as a 3-to-2 spin-orbit resonance. For every 2 orbits Mercury completes around the Sun, it rotates on its axis exactly 3 times. Here, the paradox of a Mercurian day begins to unfold. A solar day, the time from one noon to the next, is a combination of rotation and orbit. Because Mercury rotates so slowly while orbiting so quickly, the two motions are in a quiet competition. The result is that a single solar day on Mercury, the time it takes for the Sun to return to the same spot in the sky, lasts for 176 Earth days. A year on Mercury is 88 Earth days long. A day is 176 Earth days long. A single day on this planet is twice the length of its year. This extraordinary temporal dissonance is the first piece of the puzzle. The slow rotation and the rapid orbit create the conditions for the Sun's unusual behavior, but they do not, by themselves, explain why it would move backward. For that, we need the second piece: the planet's wild, lopsided orbit. The wild, lopsided orbit. Planetary orbits are rarely perfect circles. We often picture them that way, but most deviate slightly. Mercury's orbit, however, is an exception in its extremity. Of all the planets in our solar system, it follows the most eccentric, or egg-shaped, path. This is not a minor quirk. It is the force behind the planet's most unfamiliar behaviors. An orbit's eccentricity measures its deviation from a perfect circle. Earth's value is a very small 0.017. Mercury's, by contrast, is 0.2056, more than 12 times greater. This means its distance from the Sun changes dramatically. At its farthest point, or aphelion, Mercury is about 70 million kilometers away. But at its closest point, perihelion, it swings into just 46 million kilometers. One of the fundamental rules of orbital mechanics, described by Johannes Kepler, is that a planet moves fastest when it is closest to its star and slowest when it is farthest away. As Mercury falls toward the Sun, gravity accelerates it. As it climbs away, gravity slows it down. The variation in speed is significant. At its slowest, Mercury travels at about 39 kilometers per second. But as it nears perihelion, it accelerates to nearly 59 kilometers per second. This changing velocity is the second critical piece of the puzzle. A planet that rotates at a constant, slow pace, but moves through space at a wildly inconsistent speed. The historical significance of this orbit is also profound. In the 19th century, astronomers noticed its perihelion point was slowly advancing in a way that Newtonian physics could not fully account for. The discrepancy was tiny, about 43 arcseconds per century, but it pointed to a gap in our understanding. The solution did not arrive until 1915, when Albert Einstein showed his theory of general relativity perfectly predicted the shift. The curvature of spacetime by the Sun's gravity was causing the orbit to change. Mercury's unusual orbit, therefore, not only produces a strange sight in its sky, but it also holds a quiet place in the history of science, as the first confirmation of Einstein's ideas. The revelation. When orbit overtakes rotation. The explanation for the Sun's backward motion is found near perihelion, the point of Mercury's closest and fastest approach to the Sun. Here, we must consider not just linear speed, but angular speed, the rate an object appears to move across an observer's sky. The apparent motion of the Sun from a planet's surface is the result of two competing movements. The planet's rotation on its axis pushes the Sun westward, causing sunrise and sunset. Its orbital motion, at the same time, causes the Sun to drift eastward against the background of stars. On Earth, rotation is so dominant that we do not notice the eastward drift. On Mercury, the balance is far more delicate. Mercury rotates at a constant, slow rate. Its angular rotational velocity does not change. Its angular orbital velocity, however, changes dramatically. As Mercury plunges toward perihelion, its linear speed increases, and because it is also closer to the Sun, its angular orbital velocity increases even more. For most of its 88-day year, rotation wins the battle, and the Sun moves slowly west. But for a period of about 8 Earth days around perihelion, this changes. Mercury is moving so quickly in its orbit that its angular orbital velocity, the eastward push, briefly becomes greater than its constant angular rotational velocity, the westward push. The eastward motion of the orbit temporarily overpowers the westward motion of the spin. As a result, the Sun appears to stop its westward journey and begin moving backward to the east. This retrograde motion, sometimes called the Joshua phenomenon, continues until Mercury pulls away from perihelion and slows down, allowing rotation to become dominant once more. The Sun then stops a second time and resumes its slow forward march. The experience of this would depend entirely on one's location. An observer at certain longitudes would witness a stunning double sunrise, seeing the Sun rise, dip back below the horizon, and then rise a second time. At 2 specific points on the equator, known as the hot poles, the Sun would appear to stop directly overhead, swell in size, perform its backward loop for several Earth days, and then finally continue on its way. The scars of a strange sun. The effects of Mercury's unusual orbit are not confined to its sky. They are imprinted on the planet's surface. This strange rhythm has shaped its geology in profound ways. The most striking evidence is the Calauries Basin, a vast impact crater stretching 1,550 kilometers across. Its name means basin of heat, and its location is not an accident. It sits near one of the 2 hot poles, the points on the equator that face the Sun directly during perihelion. At every other close approach, the basin is positioned under that enormous, stationary Sun, causing surface temperatures to soar to 427 degrees Celsius, 800 degrees Fahrenheit. If you travel to the exact opposite side of the planet from Calauries, its antipode, you find a landscape that for decades was a mystery. First seen by the Mariner 10 spacecraft in 1974, the region was informally named the Weird Terrain. It is a chaotic, jumbled landscape of hills and fractures. The leading explanation is that this terrain is a direct consequence of the Calauries impact. When the asteroid struck Mercury, it sent powerful seismic waves through the planet's core. These waves converged at the antipode with enough focused energy to literally shake the ground apart, fracturing the crust. Mercury wears the evidence of its history on its surface. It serves as a record of external impacts, but also of the internal stresses created by its particular relationship with the Sun. With no real atmosphere to distribute heat, the temperature swings are the most extreme in the solar system, plunging to -180 degrees Celsius, -290 degrees Fahrenheit, during the long night. This brutal cycle of heating and cooling adds immense thermal stress to the surface, likely contributing to its fractured state. So we return to an observer on Mercury, watching the Sun move backward across the sky. The explanation is not a single, simple fact, but the result of several interconnected conditions. It begins with a slow rotation, locked in a 3-to-2 rhythm with its year, which creates a day far longer than its year. To this, we add a highly eccentric orbit, which causes the planet's speed to change dramatically. At its fastest point, Mercury's motion through space temporarily overtakes its own spin, causing the Sun to reverse its course. We have seen how this is more than a visual curiosity. Its effects are etched into the planet's geology, from the scorching Calauries Basin to the shattered terrain at its antipode. The story of Mercury is a reminder that our solar system is not a uniform collection of predictable bodies. It is filled with variety and complexity. Each world has its own history and its own rhythm. Mercury's backward-moving Sun shows that even within our own cosmic neighborhood, there are phenomena that challenge our Earth-centric ideas of normal. It reminds us that what feels normal is often just a small, surviving slice of what is possible. The planet where the Sun moves backwards. On most worlds, the Sun follows a simple path. It rises in the east, and it sets in the west. It is a rhythm so fundamental to our perception of time that we have built our lives around it. But on the first planet from the Sun, Mercury, that rhythm is different. The Sun there follows a quieter, stranger rule. It rises, slows to a stop in the sky, and then moves backward for a time, before resuming its gentle forward journey. This is not a hypothetical. It is a real, observable motion. The story of why it happens reveals one of the most unusual celestial dances in our solar system. A quiet puzzle of gravity and speed that took a very long time to understand. To see this impossible sunrise, we have to unravel the nature of time on a world that follows its own set of expectations. The quiet mystery. Imagine standing on the gray, dusty surface of Mercury. The ground is a landscape of extremes, shaped by impacts over billions of years. From here, the Sun would be a quiet, overwhelming presence in the black sky, appearing more than 3 times larger than it does from Earth. The light it casts would be up to 7 times more intense. You are standing on a world that has been known since ancient times, a point of light the Greeks called Hermes, after the swift messenger of the gods, a recognition of how quickly it moves across our sky. But the real story is not how fast Mercury moves through our sky. It is how slowly the Sun moves through its sky. The day begins, as any other might, but in extreme slow motion. The Sun appears over the horizon, a large orb of fire, and begins a slow ascent. But then, something unusual unfolds. At certain places on the planet, and at a specific time in its year, the Sun halts its climb. It hangs motionless, before appearing to drift back toward the horizon it just left. After this brief, backward journey, it stops again, and resumes its forward march. This is known as apparent retrograde motion. It is an illusion, but a powerful one. The planet does not actually change its spin. For a long time, this was a deep mystery. Early astronomers struggled with Mercury. Until 1965, the common idea was that Mercury was tidally locked, always showing the same face to the Sun, much like our Moon does to Earth. If that were true, one side of Mercury would be in permanent day, the other in permanent night. The Sun would not rise or set at all, but hang fixed in the sky. But this idea was incorrect. In 1965, using radar observations from the Arecibo Observatory, astronomers found something new. By bouncing radio waves off the planet, they discovered that Mercury was not locked. It was spinning, but at a speed that made little intuitive sense. It completed one rotation in about 59 Earth days. This discovery slowly began to change the picture. Mercury had its own day, but its length was strangely connected to its year, the 88 Earth days it takes to orbit the Sun. Here were the clues. A day that was 2/3 of its year, an orbit that was more stretched and elliptical than any other planet's, and a Sun that appeared to move backward. These were not separate facts. They were connected pieces of a single, quiet puzzle. To solve the mystery of the backward-moving Sun, we first have to understand the strange relationship between a day and a year on this world. And to do that, we need to look again at what a day even means. Orbits and rotations. On Earth, our sense of a day and a year feels simple. A year is one trip around the Sun. A day is one spin of our planet. But beneath this simplicity lies a quiet detail, one that is important for understanding Mercury. We have 2 kinds of day. A sidereal day and a solar day. A sidereal day is the time it takes for a planet to make one full 360-degree turn relative to the distant stars. For Earth, this is 23 hours and 56 minutes. You might think, but a day is 24 hours. And that is also true. We live our lives by the solar day which is the time it takes for the Sun to return to the same position in the sky, from one noon to the next. The 4-minute difference exists because while the Earth is spinning, it is also moving along its orbit. After one full spin, a sidereal day, Earth has moved a little forward. To get the Sun back to the same place in our sky, our planet has to rotate just a little bit more. On Earth, this difference is small. On Mercury, this difference is everything. Let's look at the numbers for Mercury. As we established, its sidereal day, one full spin, is 58.6 Earth days long. Its year, one orbit, is 87.97 Earth days long. Immediately, we see an unusual relationship. 58.6 is almost exactly 2/3 of 87.97. This is not a coincidence. This is the heart of the mystery. This brings us to the first major piece of the puzzle: Mercury's orbit. All planets move in ellipses, not perfect circles, but Mercury's path is the most eccentric, or egg-shaped, of any planet in our solar system. Its distance from the Sun changes significantly, from as close as 46 million kilometers to as far as 70 million kilometers. This detail has a profound effect on its speed. According to Kepler's second law, a planet moves fastest when it is closest to the Sun, perihelion, and slowest when it is farthest away, aphelion. As Mercury slingshots around the Sun at perihelion, its orbital speed is at its highest. When it glides through the far end of its orbit, it moves at its most leisurely pace. So, we have two important motions at play. First, a constant, steady spin, one rotation every 59 Earth days. Second, a highly variable orbital speed. It is the interplay between these two motions, the steady spin and the unsteady orbit, that sets the stage for the Sun's unusual performance. The fixed rhythm of the planet's rotation is in a quiet dialogue with the changing rhythm of its journey through space. This dialogue creates a celestial illusion, where from the surface of Mercury, the Sun itself seems to change its pace, and even its direction. But why the system settled into this strange rhythm is a story about gravity. The 3-2 spin orbit resonance. So we have the clues: a slow, steady spin and a fast, variable orbit. How do they combine to create a backward-moving Sun? The answer is found in a quiet principle of celestial mechanics known as spin-orbit resonance. This happens when a body's rotation becomes locked in a simple ratio with its orbit around another. Think of gently pushing a child on a swing. You time your pushes to match the rhythm of the swing's motion. The Sun's gravity does something similar. Its immense pull tugs on Mercury, and over billions of years, these tugs have guided the planet's spin into a stable, repeating pattern. The most common form of this is a 1-to-1 resonance, or tidal locking. This is what happened with Earth's moon. The moon rotates exactly once for every single orbit it makes around Earth. For a long time, astronomers assumed this was Mercury's fate as well. It is often the most stable arrangement for a planet so close to its star. So why did it not happen? The reason is Mercury's highly eccentric orbit. The Sun's gravity pulls more strongly on the side of Mercury facing it than on the far side. This difference creates a slight bulge in the planet's shape, stretching it into a very subtle football-like form. This bulge acts like a quiet handle that the Sun's gravity can grip, guiding the planet's rotation. If Mercury's orbit were nearly circular, these tidal forces would have eventually slowed Mercury's spin into a 1-to-1 lock. But because its orbit is so elliptical, the strength of these forces changes dramatically. When Mercury is far from the Sun, the forces are weak. But as it swings in for its close approach at perihelion, the Sun's gravitational pull intensifies. This powerful gravitational kick is the most important part of the conversation between the Sun and Mercury. Because Mercury's orbital speed changes so much, a perfect 1-to-1 lock would be unstable. So, instead of locking into that rhythm, Mercury settled into something else. A more complex, but incredibly stable, harmony. It settled into a ** 3-2 spin orbit resonance. This means that for every *2* times Mercury orbits the Sun, it rotates on its axis exactly *3* times. It is a kind of cosmic gear system. For every 2 revolutions of the large, orbital, gear, the smaller, rotational, gear turns 3 times. This specific rhythm creates a special stability. At perihelion, when Mercury is moving fastest and the Sun's tidal forces are strongest, the planet's rotation and orbit are almost perfectly in sync. This is the moment where gravity has the most influence, and the 3:2 resonance allows Mercury to present itself to the Sun in a consistent way, orbit after orbit. This discovery in 1965, first proposed by scientist Giuseppe Colombo, was a revelation. The spin was not random, it was a deeply ordered state, born from the unique combination of Mercury's path and its closeness to the Sun. It was not chaos. It was a kind of clockwork, a celestial dance choreographed by gravity itself. This precise 3:2 timing is the direct cause of the Sun's strange retrograde motion. Now, we can return to the surface and see how this quiet rhythm translates into an impossible optical illusion. Reconstructing the retrograde Sun. With the 3:2 spin-orbit resonance as our key, we can now understand the case of the backward-moving Sun. The illusion is born from the interplay between 2 different speeds: Mercury's constant rotational speed and its changing orbital speed. An observer on the surface is carried by 2 motions at once. The first is the planet's spin, which makes the Sun appear to move across the sky from east to west. This is a steady, constant motion. The second is the planet's orbit. As Mercury moves, the direction to the Sun also changes, which affects the Sun's apparent position. Most of the time, the planet's spin is the stronger influence. At aphelion*, where Mercury is farthest from the Sun and moving slowest, the spin easily wins. The Sun appears to crawl across the sky in the normal direction, just very, very slowly. But as Mercury falls back towards the Sun, its orbital speed increases. Faster and faster it moves. For an observer on the surface, the Sun's westward motion begins to slow down. This is because the orbital motion, the planet itself moving forward, is starting to cancel out some of the apparent drift caused by rotation. Then comes the critical moment. For about 8 Earth days around perihelion, something extraordinary happens. Mercury's orbital angular velocity, how fast it is moving along its path, becomes greater than its rotational angular velocity. For this brief window, the effect of the planet's forward motion overpowers the effect of its spin. Imagine you are on a very slowly rotating platform that is being carried on a high-speed track. Normally, you see the world outside moving past you because of the platform's spin. But if the track suddenly accelerates to a speed faster than the edge of the platform is turning, the world outside would appear to move backward relative to you. You are moving forward so fast that you overtake the apparent motion created by your own spin. This is what happens on Mercury. From the surface, the Sun, which had been moving slowly from east to west, appears to stop. Then, as orbital speed outpaces spin, the Sun begins to move in reverse, from west to east. This is the apparent retrograde motion. The Sun has not changed course, and Mercury has not changed its spin. It is an optical illusion created by the interplay of these 2 speeds. After Mercury passes perihelion, its orbital speed starts to decrease again. The Sun appears to stop its backward motion, and then, as the spin once again becomes dominant, it resumes its slow journey from east to west. This happens every Mercurian year. But where you are on the planet determines what you see. For some, the Sun performs this loop high in the sky. But for others, at just the right longitudes, this event happens near sunrise or sunset. These locations witness the double sunrise. The Sun will rise, hang there, then dip back below the horizon as it moves backward, only to rise a second time once it resumes its forward motion. It is a quiet, looping light show, all orchestrated by the planet's unusual dance with the Sun. A day that lasts 2 years. The 3:2 resonance does more than create an unusual sunrise. It quietly reshapes the very idea of time on Mercury. The most striking consequence is the length of a solar day, the time from one noon to the next. Because of the 3:2 resonance, one solar day on Mercury lasts for 176 Earth days. It takes exactly 2 full trips around the Sun for the Sun to return to the same position in Mercury's sky. This means a single day on Mercury is twice as long as its year. A year passes, then another, all within the space of a single day-night cycle. One side of the planet is in continuous sunlight for about 88 Earth days, while the other side is in an equally long night. This incredibly long solar day creates the most extreme temperature differences in the solar system. During the long day, the surface can reach 430 degrees Celsius. But during the equally long night, with no atmosphere to hold heat, the temperature falls to -180 degrees Celsius. Mercury is a world of fire and ice, existing side by side. This extreme heating and cooling has shaped the planet. The largest impact crater, the Calori's Basin, is named from the Latin word for heat. Its location means it is directly under the Sun during perihelion on every second orbit, making it one of the hottest places on the planet. The thermal stress from the long days and nights has caused the surface to wrinkle, creating enormous cliffs called scarps. And yet, even on this world of fire, there is a place for ice. The planet's axis has almost no tilt. This means the floors of deep craters at the poles are in permanent shadow. In these cold, dark pockets, water ice can persist for billions of years. NASA's MESSENGER mission confirmed the presence of this ice, a quiet discovery on a planet so close to the Sun. It is another of Mercury's paradoxes, a world hot enough to melt metal, yet home to frozen water. The cosmic context. Mercury's 3:2 resonance makes it unusual among the planets, but these gravitational harmonies themselves are a common feature in the cosmos. Most large moons in our solar system, including our own, are in a simple 1:1 resonance. This is the most common end state for bodies orbiting close to a much larger parent. Mercury stands apart because its eccentric orbit guided it into a more complex, but equally stable, arrangement. Its story is a perfect illustration of how a few initial conditions can lead to a very different evolutionary path. If Mercury's orbit had been circular, the spectacle of the backward-moving Sun would not exist. Looking elsewhere, we see other quiet oddities. Venus has a day longer than its year and rotates backward. The cause is still debated. The point is, our solar system is not a uniform collection of spheres. Each world is a product of its history, shaped by gravity, chance, and time. The story of Mercury's spin is a testament to the quiet and often counterintuitive solutions that emerge from the laws of physics. It reminds us that the rhythms of the cosmos are far stranger than we might imagine from our own world. What once seemed to be a planet that broke the rules turned out to be a perfect expression of those rules, unfolding in an unfamiliar way. The backward-moving Sun of Mercury is more than a cosmic quirk. It is the quiet, visible result of a hidden harmony between a planet's spin and its journey through space. It is a story written in the language of gravity, where an eccentric orbit and powerful tidal forces created a rhythm found nowhere else in our solar system, the stable, hypnotic 3:2 spin-orbit resonance. From this single principle, all of Mercury's strangeness flows. The day that lasts 2 years, the double sunrises, and the extreme temperatures. It is a powerful reminder that the universe is filled with wonders that challenge our everyday intuition. The simple act of a sunrise, something we take for granted, can become a bizarre, week-long spectacle on another world. If this kind of calm exploration into our solar system helps you unwind, consider liking the video and subscribing to the channel. And let us know in the comments if there is another quiet corner of the cosmos you would like to explore. In the silent mechanics of our solar system, each planet follows a rhythm defined by gravity and time. We have grown accustomed to the rhythm of our own world. Its steady rotation gives us the cycle of day and night. Its long orbit gives us the seasons. It is a predictable pattern, one that has shaped biology, history, and our perception of what is normal. But elsewhere in the solar system, other worlds follow different patterns. There is a planet where the familiar sequence of sunrise, noon, and sunset is quietly broken. A place where the sun, from the perspective of an observer on the surface, appears to pause, move backward, and then resume its journey. This is not a concept from fiction. It is a real and observable phenomenon on the planet closest to our sun. This is the rhythm of Mercury. Imagine standing on a silent, cratered surface. The sun begins to rise, but its ascent is unusually slow. As it climbs, it seems to grow larger in the sky. Then, it appears to stop. For a time, it hangs motionless. And then, something unexpected happens. The sun begins to move backward, retreating toward the horizon from which it came. After a time, it halts its reverse motion, and once again begins to move slowly across the sky. This is what a day can look like on the planet Mercury. The question is not if this occurs, but how. What quiet combination of orbital mechanics and gravitational resonance could create a sunrise that seems to play in reverse? The answer is found in a story of gravitational harmony, an unbalanced orbit, and a timing so precise it reveals the subtle complexity of planetary motion. The familiar rhythm, day and year on Earth. To understand the strangeness of Mercury, we must first look to the familiar. The words, day, and year, carry with them a set of assumptions based on our experience on Earth. On Mercury, those assumptions no longer apply. On Earth, a day is the time it takes for the planet to complete one rotation on its axis. This cycle of light and dark is fundamental to our measurement of time. Yet even this concept has two distinct definitions. There is the sidereal day asterisk, which is one full rotation measured against the fixed background of distant stars. This takes approximately 23 hours and 56 minutes. But our lives are governed by the sun. This brings us to the solar day asterisk, which is the time it takes for the sun to return to the same position in the sky, for instance, from one noon to the next. This is our familiar 24-hour day. The 4-minute difference is a consequence of Earth's second motion, its orbit. As Earth spins, it is also moving along its orbital path. Each day, it travels a small distance around the sun. After it has completed a full 360-degree rotation relative to the stars, a sidereal day, its orbital movement means it has to rotate just a little further to bring the sun back to the same position. That small extra rotation takes about 4 minutes, giving us our 24-hour solar day. Our concept of a day is a product of both our rotation and our orbit. Our year is the time it takes for Earth to complete one orbit, a journey of roughly 365.25 days. Our planet's orbit is not a perfect circle, but it is close to one. The distance to the sun varies only slightly, and this variation is not the primary cause of our seasons. The seasons are instead caused by our planet's axial tilt, the 23.5-degree angle of its spin. For half the year, one hemisphere is angled more directly toward the sun, experiencing summer, while the other is angled away, experiencing winter. The situation then reverses. This is the earthly model. A fast rotation combined with a much longer orbit gives us a short solar day and a long year. A nearly circular orbit and an axial tilt give us predictable seasons. Everything is orderly. This is our baseline for normal. Now, we travel inward, closer to the sun, to a world that follows a different set of rules. An unfamiliar world, Mercury's orbit and a history of misunderstanding. When we arrive at Mercury, our earthly assumptions about time become invalid. The numbers that govern this small, sun-scorched world are deeply counterintuitive. First, its year. Mercury is the fastest planet in the solar system. Pulled by the sun's immense gravity, it moves through its orbit at nearly 47 kilometers per second. This speed allows it to complete one full orbit, a Mercurian year, in just 88 Earth days. An observer on Mercury would experience a new year approximately every 3 months. Now, for its day. One might expect a planet so close to the Sun to spin rapidly. The reality is the opposite. Mercury rotates on its axis with remarkable slowness. It takes 58.65 Earth days to complete one rotation relative to the stars. This is its sidereal day. A year on Mercury is 88 Earth days long. A single rotation takes nearly 59 Earth days. The planet rotates so slowly that its rotational period is almost exactly 2/3 of its orbital period. This is not a coincidence. It is the key to its unusual solar cycle. For a long time, astronomers misunderstood Mercury. Its proximity to the Sun makes it difficult to observe from Earth, as it is often lost in the glare. Early observers, catching glimpses of the planet at ideal times, repeatedly saw the same surface features. This led them to a logical, but incorrect, conclusion that Mercury was tidally locked to the Sun, with a rotation period equal to its orbital period of 88 days. This would mean one side of the planet was in perpetual daylight, the other in perpetual darkness. This one-to-one tidal lock theory seemed plausible. And yet, there were problems. The dark side of Mercury, observed with radio telescopes, was warmer than it should have been if it never received sunlight. Something did not add up. The mystery was solved in 1965 at the Arecibo Observatory. Scientists bounced radar signals off Mercury's surface. By analyzing the Doppler shift of the returning signal, they could measure the planet's rotation speed directly. The result was a surprise. Mercury was not in a one-to-one lock. It was spinning, but with a period of approximately 59 days. It was the Italian scientist Giuseppe Bepi Colombo who realized the significance of this number. 59 is almost exactly 2/3 of 88. Mercury was not in a one-to-one spin-orbit resonance, but a more complex 3-to-2 resonance. It rotates on its axis exactly 3 times for every 2 orbits it makes around the Sun. This discovery changed our understanding of the planet and provided the foundation for explaining its strange solar day. It turns out that a day on Mercury, the time from one sunrise to the next, is a staggering 176 Earth days long, exactly 2 Mercurian years. The reason is found in the intricate relationship between that slow spin and that fast orbit. The 3-to-2 resonance, the mechanics of a 176-day sun. The term 3-to-2 spin-orbit resonance describes a form of gravitational harmony. In this arrangement, Mercury completes 3 rotations on its axis for every 2 times it circles the Sun. This is the precise, stable, and deeply strange dance Mercury performs. Let us trace this motion step by step. We can place an observer on Mercury's surface, at a point where the Sun is directly overhead. Mercury begins its orbit. Its year is 88 Earth days. Its sidereal day, one full rotation, is 58.65 Earth days. After 58.65 days, Mercury has completed one full rotation. The observer is again facing the same direction relative to the distant stars. In that same time, however, the planet has traveled 2/3 of the way through its orbit. The Sun is no longer overhead. The slow rotation has not kept pace with the rapid orbital motion. At the 88-day mark, Mercury has completed its first full orbit. In that time, it has completed exactly 1.5 rotations on its axis. The observer is now facing directly away from the Sun. It is midnight. One full Mercurian year has passed, but it has only been half of a Mercurian solar day. Now for the second orbit. After another 88 days, a total of 176 Earth days from the start, Mercury has completed its second full orbit. In that time, it has completed a total of 3 full rotations. The observer, having spun around 3 times while circling the Sun twice, is now once again facing directly toward the Sun. High noon has returned. One solar day on Mercury, the time from noon to noon, has taken 176 Earth days. In that period, the planet has orbited the Sun twice. A single day is twice as long as a year. This is the direct consequence of the 3:2 resonance. On Earth, our fast rotation easily outpaces our orbital motion. But on Mercury, the spin is so slow and the orbit so fast that the planet's own movement around the Sun dramatically alters the Sun's apparent position. This stable resonance is the result of tidal forces from the Sun acting on Mercury over billions of years. A perfectly circular orbit might have led to a simpler one-to-one lock. But Mercury's orbit is not circular. And it is this final element, its eccentric orbit, that turns the strange 176-day solar cycle into something truly remarkable. The elliptical path. How an unbalanced orbit reverses the Sun. We have established the timing of Mercury's day. A 3:2 spin orbit resonance that stretches a single solar day across 2 Mercurian years. Now we add the final element that produces the apparent backward motion of the Sun. This element is Mercury's orbit. Unlike Earth's nearly circular path, Mercury's orbit is highly eccentric, or oval-shaped. At its farthest point, aphelion, it is about 70 million kilometers from the Sun. At its closest point, perihelion, it swings in to just 46 million kilometers. This varying distance affects Mercury's speed, as described by Kepler's second law of planetary motion. A planet moves fastest when it is closest to its star and slowest when it is farthest away. As Mercury approaches perihelion, its orbital velocity increases dramatically. Here, two motions come into conflict: Mercury's steady rotation on its axis, and its variable speed as it orbits the Sun. The speed of Mercury's spin is more or less constant. It turns at the same slow rate of one rotation every 58.65 Earth days. Its orbital velocity, however, is not constant. For most of its year, the effect of its rotation is faster than the effect of its orbital motion on the Sun's apparent position. The Sun appears to move steadily across the sky from east to west. But for a brief period of about 8 Earth days around perihelion, when Mercury is closest to the Sun and moving fastest, its orbital speed effectively overtakes its rotational speed. From the surface, the Sun's westward motion is the result of the planet's eastward rotation. But the planet's orbital motion also causes an apparent eastward drift of the Sun against the background stars. Near perihelion, Mercury is moving so fast that this eastward drift caused by its orbit becomes greater than the westward motion caused by its slow spin. From the perspective of an observer, the Sun's westward journey halts. The two competing motions cancel each other out, and the Sun hangs motionless. Then, as the orbital motion continues to dominate, the Sun begins to move backward from west to east. This retrograde motion continues for a few Earth days. As Mercury pulls away from the Sun, its orbital velocity decreases. The Sun slows its backward travel, stops a second time, and then resumes its normal westward course as the rotational motion once again becomes the dominant factor. The visual experience of this event depends on one's location on the planet. For some observers, the Sun rises, pauses, dips back below the horizon, and then rises a second time to begin its long journey across the sky. At other locations, this effect happens around noon. An observer there would see the Sun approach its highest point, move backward while growing larger and brighter as Mercury rushes toward perihelion, then stop and move forward again, shrinking as the planet recedes. This is not an illusion, but a real geometric effect born from the unique combination of Mercury's 3:2 resonance and its eccentric orbit. It is a quiet demonstration of how the laws of physics can produce profoundly unfamiliar outcomes. This journey into the quiet mechanics of Mercury reveals a universe far more varied than we might imagine from our own world. It shows us that even a concept as fundamental as the rising and setting of the sun is not universal. Every planet has its own story, its own rhythm. If this kind of calm exploration into the workings of the cosmos helps you unwind, consider subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're listening from. There are countless other worlds, and their stories are waiting to be told. So, we return from our imaginary journey to Mercury with a deeper appreciation for the intricate clockwork of the solar system. The case of the backward-moving sun is not a defiance of physics. It is a perfect demonstration of physics operating under unusual conditions. It is the result of a precise gravitational lock, the 3:2 spin-orbit resonance, which dictates that a day on Mercury lasts for 2 of its years. And it is the consequence of a lopsided orbit, which causes the planet's orbital speed to periodically overwhelm its rotational speed, creating the apparent retrograde motion of the Sun. The story of Mercury is also a lesson in how science works. It shows how a long-held assumption, the one-to-one tidal lock, can be corrected by new data from a new instrument, like the Arecibo radio telescope. It reminds us that our understanding of the universe is always evolving. The journey from thinking Mercury's day was equal to its year, to discovering the 3:2 resonance, and to finally modeling how that resonance combines with an eccentric orbit, is a testament to the scientific process itself. On Earth, we look up at a sun that behaves with comforting regularity. But on Mercury, the sun is a more dramatic character. It swells and shrinks, it pauses, and it reverses course. It puts on a daily performance that serves as a quiet reminder of the diversity of worlds. It tells us that our earthly experience is just one of many possible choreographies in the silent ballet of the planets. The universe is not bound by our sense of normal. The planet where the sun moves backward is not an anomaly to be dismissed. It is a treasure to be understood, a celestial object shaped by the subtle and powerful forces of gravity and time. The planet where a day lasts longer than a year. On Earth, our experience of time follows a simple, reliable rhythm. The sun rises and sets, and a day passes. These days fit neatly into the larger cycle of a year. It is a pattern so fundamental that it feels like a universal rule. But in our own solar system, there is a planet where this rule is broken. A world where a single day lasts longer than its entire year. This is not a concept from fiction. It is the quiet reality of the sun's closest companion, Mercury. This is a calm exploration of that scorched and quiet world, a place where the passage of time is unfamiliar, and where the sun can appear to rise twice in the same long morning. Imagine standing on a still, cratered surface. You look toward the horizon for the sunrise, an event that will not happen again for 176 Earth days. The sun, which appears much larger than it does from Earth, begins a slow climb into a black and airless sky. But then, something unusual happens. The sun seems to pause. It hangs motionless for a time before it begins to move backward, retreating toward the horizon it just left. After this quiet retreat, it pauses once more, and then finally resumes its slow journey across the sky. This is a sunrise on Mercury. And to understand how it can happen, we need to look at the subtle mechanics of a planet that moves to its own rhythm. At first glance, Mercury seems to be a planet defined by speed. It was named for the swiftest of the ancient Roman gods, and it is the fastest planet in our solar system. It moves through space at an average speed of nearly 47 kilometers per second, completing a full orbit around the Sun in just 88 Earth days. This is its year. Yet the time from one sunrise to the next, what astronomers call a solar day, lasts 176 Earth days. A single day-night cycle on Mercury is twice as long as its year. You would experience 2 full Mercurian years in the span of a single Mercurian day. This quiet paradox is the result of a particular relationship between Mercury's rotation on its axis and its journey around the Sun. To understand it, we need to separate the idea of a day into two distinct concepts: the sidereal day and the solar day. For us on Earth, the difference is small. For Mercury, the difference is everything. Our journey into the clockwork of Mercury begins with its spin. It takes approximately 59 Earth days for Mercury to complete one full rotation on its axis relative to the distant stars. This is its sidereal day. This slow rotation is a consequence of the immense gravitational pull of the Sun. Being so close to our star, Mercury experiences powerful tidal forces that have acted as a brake over billions of years, slowing its spin from what was likely a much faster rate in its past. For a time, astronomers believed Mercury was tidally locked, with one side always facing the Sun. But in 1965, radar observations revealed something more complex and far more interesting. Mercury is not fully tidally locked. Instead, it exists in what is called a 3-to-2 spin orbit resonance. This is the first part of the explanation. It means that for every 2 orbits Mercury completes around the Sun, it rotates on its axis exactly 3 times. 2 Mercurian years are equal to 3 Mercurian sidereal days. This stable, rhythmic relationship is the foundation for the strange temporal effects on the planet. After one orbit of 88 days, Mercury has rotated 1.5 times. The side that was facing the Sun at the start of the year is now facing directly away from it. After the second orbit is complete, at 176 Earth days, the planet has spun a total of 3 times, and the original side is once again facing the Sun. This 176-day interval, the time it takes for the Sun to return to the same position in the sky, is Mercury's solar day. And there is the solution to the paradox. The solar day is twice the length of the year because of this 3-to-2 resonance. A Mercurian year is 1 lap around the Sun. A Mercurian day is the time it takes the Sun to appear in the same spot again, which requires 2 full laps. But this only explains the length of the day. It does not explain the spectacle of the Sun stopping and moving backward. For that, we need to add a second element: Mercury's unusual, egg-shaped orbit. Planetary orbits are not perfect circles. They are ellipses. Most planets in our solar system, however, have orbits that are very close to circular. Mercury is the exception. It has the most eccentric, or elongated, orbit of all the planets. Over its 88-day year, its distance from the Sun changes significantly. At its farthest point, it is about 70 million kilometers from the Sun. But at its closest point, perihelion, it is just 46 million kilometers away. This changing distance affects its orbital speed. A planet moves faster when it is closer to the star it orbits. As Mercury swings in toward perihelion, its orbital velocity increases. Then, as it pulls away, it slows down. This change in speed is the key to the Sun's backward motion. The apparent movement of the Sun across a planet's sky is a combination of 2 things: the planet's rotational speed and its orbital speed. On Mercury, the balance between these two is delicate. Its rotation is slow and constant, while its orbital speed changes dramatically. For most of its orbit, the rotation is faster than the effect of its orbital motion, so the Sun appears to move slowly across the sky as expected. But as Mercury approaches perihelion, its orbital speed increases so much that for a brief period, it actually overtakes its rotational speed. The planet is still spinning in the same direction, but its movement along its orbit is so fast that it outpaces the spin. From the surface, this causes the Sun to appear to move backward in the sky. The planet's forward journey around the Sun temporarily becomes more powerful than its own slow turn. Let us put these pieces together and follow a full solar day on Mercury, a journey that lasts 176 Earth days. It begins in a deep and profound darkness. With no real atmosphere to hold heat, the night side of Mercury cools to temperatures as low as -180 degrees Celsius. The sky is a perfect, still black. This night lasts for 88 Earth days, an entire Mercurian year. After this long night, a faint glow appears on the horizon. The Sun, appearing much larger than it does in our sky, begins its ascent with an unfamiliar slowness. The gray, cratered landscape is gradually revealed. Then, as Mercury nears its closest approach to the Sun, the strange motion begins. At certain longitudes, an observer would see the Sun's progress come to a halt. It hangs suspended in the black sky. As Mercury moves through its closest point, its orbital speed exceeds its rotational speed. The Sun then appears to move in reverse, drifting back toward the horizon. This quiet retrograde motion continues for a few Earth days. Then, as Mercury pulls away from the Sun and its orbital speed decreases, the backward motion slows. The Sun stops a second time, and then resumes its slow, forward journey across the sky. Now, the true Mercurian day begins. For the next several weeks, the Sun crawls across the sky. With no atmosphere for protection, the surface temperature rises to around 430 degrees Celsius, hot enough to melt lead. This side of the planet becomes one of the hottest places in the solar system. After about 88 Earth days of continuous daylight, the Sun approaches the western horizon. As darkness returns, the temperature begins to fall almost instantly, back toward the deep cold of the long night. The cycle, all 176 days of it, is complete. You have lived through 2 years in a single day. This day-year cycle is more than a curiosity, it shapes the entire planet. The extreme temperature swing, a range of about 600 degrees Celsius, is the largest of any planet in our solar system. This thermal stress has likely helped shape Mercury's geology, causing its crust to buckle and crack, creating long cliffs called scarps that cross the surface. One of the most prominent features on Mercury is the Calori's Basin, a huge impact crater about 1,550 kilometers wide. It happens to be located in a region that faces the Sun directly during some of the planet's closest passes, exposing it to the most intense heating. On the exact opposite side of Mercury from this basin lies a region of jumbled, broken hills known as the weird terrain. This is thought to have been formed by seismic shockwaves from the Calori's impact, which traveled through the planet and converged at the other side, shattering the crust. Yet, on this world of fire, there is also ice. Mercury's axis has almost no tilt, meaning it spins nearly perfectly upright. Because of this, the floors of some craters at its north and south poles are in permanent shadow. They never see sunlight. In these cold, perpetual nights, temperatures can remain low enough for water ice to exist. Observations have confirmed that these shadowed craters do contain deposits of ice. It is a quiet paradox. The planet closest to the Sun harbors frozen water in places of eternal darkness. Unlocking the secrets of Mercury has been a slow process. Sending a spacecraft there is difficult. A probe must constantly fight the Sun's immense gravity to enter orbit. Any spacecraft must also be protected from intense heat and radiation. For these reasons, Mercury has been one of the least visited planets. The first mission was NASA's Mariner 10, which flew by 3 times in 1974 and 1975. It gave us our first close-up images but was only able to map about 45% of the surface. For decades, the rest of Mercury remained unseen. That changed in 2011 when NASA's Messenger spacecraft became the first probe to orbit the planet. For 4 years, Messenger mapped the entire surface, analyzed its composition, and confirmed the presence of water ice. Its precise measurements gave us the data needed to fully understand the dynamics of Mercury's day and year. The exploration is not over. A new chapter is unfolding with the Bepi-Colombo mission, a joint project of the European Space Agency and the Japan Aerospace Exploration Agency. Launched in 2018, it is scheduled to enter orbit around Mercury in late 2025. Once there, two orbiters will separate to study the planet's surface, interior, and magnetic field in unprecedented detail. Bepi Colombo promises to answer lingering questions about how this quiet, extreme world came to be. From the paradox of its day and year to the spectacle of a sun that moves backward, Mercury challenges our simple assumptions about how planets behave. It is a world of extremes, shaped by its proximity to the sun. Its particular celestial rhythm is found nowhere else, and it dictates every aspect of this small, dense world. Mercury reminds us that even in our own cosmic neighborhood, there are wonders that defy our earth-bound intuition. It shows that the simple passage of a day can be a spectacle of unexpected complexity. If you enjoyed this quiet journey to one of the solar system's most unusual worlds, consider subscribing for more explorations into the cosmos. And feel free to share in the comments what other planetary mystery you would like to understand next. In our solar system, there are worlds of profound extremes. Planets where familiar rules of time, light, and temperature do not apply. Some are defined by crushing pressure, others by gaseous storms that last for centuries. And one, the closest to our Sun, is defined by a day so long and so violent, it challenges our understanding of what a planet can be. This is a journey to that world. Not as a survivor in a story, but as an observer trying to comprehend a place of sheer contrast. A planet where a single day lasts longer than its year, where the sun can rise, set, and rise again in the same morning, and where the difference between light and shadow is the difference between molten lead and frozen gas. This is an exploration of Mercury. If this kind of calm exploration into the worlds of our solar system helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a quiet town, or somewhere in between, feel free to share where you're listening from. The slow dawn. An observer's first sensation on Mercury would not be one of heat, but of a silence so absolute it feels like a physical presence. On the gray, dusty surface, the universe would seem to be holding its breath. The only sounds would be the hum of life support, a tiny bubble of noise in an ocean of quiet. Landing in the final moments of a long, cold night, a night that has lasted for weeks, the horizon would be a perfect, sharp curve against a black sky. But the most defining feature of Mercury is its relationship with time. A single day on Mercury, from one sunrise to the next, lasts 176 Earth days. This is longer than its 88-day year. An entire orbit of the Sun is completed before a single-day night cycle is over. This bizarre reality is the product of a delicate cosmic dance called a 3-to-2 spin orbit resonance. For every 2 trips it makes around the Sun, Mercury rotates on its axis exactly 3 times. This gravitational lockstep is the engine of the planet's extremes. The landing site for such a journey would be chosen with painstaking precision, likely a plain within the vast Calauries Basin, a colossal impact crater over 1,550 kilometers wide. The name means basin of heat, yet upon arrival, the temperature would read close to -180 degrees Celsius. This is a cold so deep it feels less like a temperature and more like an active force, leaching warmth from everything it touches. For the first few Earth days there would be only darkness. The ground is a monochrome landscape of grayish-brown dust, scarred by billions of years of micrometeorite impacts. Mercury has no real atmosphere to burn up incoming debris, only a whisper-thin exosphere composed of atoms like oxygen, sodium, and helium, blasted off the surface by solar wind. It offers no protection, no insulation, and no weather. In that perfect vacuum, the stars do not twinkle. They are hard, sharp points of light, burning with an intensity never witnessed from Earth. The Milky Way is a dense, textured river of light, so bright it casts the faintest of shadows. It is the greatest astronomical observatory in the solar system. Then, the sunrise begins. It is not a gentle dawn. The horizon, once a crisp black line, gains a single, impossibly bright point of light. It is the first touch of the sun's corona, peeking over the edge of the planet. And then, it seems to just sit there. The slowness is something that is difficult to describe. Imagine a sunrise where the sun moves slower than the minute hand on a clock. You do not perceive the movement, you only know intellectually that it is rising. As the sun climbs, the landscape is brought into sharp relief. It is covered in countless craters and crisscrossed by strange, winding ridges called lobate scarps. These are wrinkles on the planet's skin, formed as its massive iron core cooled and contracted over billions of years, causing the crust to buckle. Mercury is, quite literally, a shrinking planet. The light itself creates a world of stark, brutal contrast. With no atmosphere to scatter it, the sky remains black. Sunlight simply illuminates what it touches. Anything in direct light is brilliantly lit. Anything in shadow is plunged into absolute blackness. A step into a shadow is like stepping into a void. It is a landscape of pure binary, light in its complete absence. By the 20th Earth day, the temperature approaches 0 degrees Celsius. The sun is now a terrifying orb that dominates the black sky. And this is when the second act of Mercury's celestial play begins. Because of the planet's highly eccentric, egg-shaped orbit, its orbital speed changes dramatically. As it gets closest to the sun, its orbital speed starts to catch up with its incredibly slow rotation. From the ground, this creates an effect that defies logic, a double sunrise. An observer standing on a ridge would see the sun, which had been crawling upward for weeks, appear to slow to a halt. Then, impossibly, it would begin to move backward, sinking toward the horizon it had just cleared. It feels as though the universe has broken. The sun dips, and for a few surreal hours, it is as though the day is retreating. It might even set briefly before stopping its retreat and slowly, once again, beginning to rise. A sunrise, a partial sunset, and then a second sunrise. This celestial stutter is a reminder that this world operates on a completely different set of rules. By day 44, the sun is climbing towards its zenith. The real day, the day of fire, is about to begin. The long noon. The 44 Earth days it takes for the sun to reach noon are a slow descent into an inferno. The concept of a day loses all meaning. It is just a continuous, unending period of escalating heat. By the time the sun reaches its highest point in the sky, the surface temperature reaches its peak, around 427 degrees Celsius, or 800 degrees Fahrenheit. This is a temperature hot enough to melt lead into a shimmering puddle on the ground. The landscape itself transforms. Heat radiates from the ground in visible waves. Any observer would be confined to a shielded lander, as venturing outside would be an immediate thermal assault. It is not like standing in an oven, it is like being blasted by a blowtorch. From Mercury, the sun can appear up to 2.5 times larger than it does from Earth, and its light can be over 10 times brighter. The other enemy is radiation. Mercury has a global magnetic field, but it's only about 1% as strong as Earth's, providing minimal protection. The solar wind, a stream of charged particles from the sun, mostly flows around the planet, but some of it is funneled into magnetic tornadoes that slam directly into the surface. The psychological toll of this environment would be immense. Imagine being trapped in a small room for over a month, with the constant threat of overwhelming heat, surrounded by the hum of machinery under immense strain. And the sun just hangs there. At noon, its slow crawl across the sky becomes almost imperceptible. For weeks, it barely moves from its position directly overhead. There is no escape. On Earth, even on the hottest day, you know the sun will eventually set. On Mercury, there is no such promise. Noon is not a time of day, it is an epoch. Yet, there is a quiet grace in the science. During this peak heating, another strange phenomenon occurs. The Sun, which appeared largest during the double sunrise, is now slightly smaller. Mercury has moved further away from the Sun in its orbit, but its rotation is so slow that it is still noon. This means the intensity of the sunlight actually decreases slightly as the afternoon wears on, even while the Sun is still near its highest point. It is another of Mercury's orbital paradoxes. The Earth days bleed into one another. Day 60, Day 70, Day 80, the heat is relentless, the waiting is relentless, and then, slowly, almost imperceptibly, the thermal readings begin to tick downward. After 88 Earth days of scorching sunlight, the longest afternoon in the solar system finally begins to end. The rapid twilight. The transition from day to night on Mercury is not a gentle twilight. It is a catastrophic plunge. With no atmosphere to hold onto heat, the moment the sun's rays leave a patch of ground, that ground begins radiating its energy directly into space. The temperature drop is shockingly fast. The visual spectacle of the sunset is as protracted as the sunrise. The sun, a bloated, white-hot disk, sinks with agonizing slowness. The shadows, which had been tiny things huddled at the base of rocks, begin to stretch, becoming black daggers creeping across the incandescent landscape. Watching those shadows is mesmerizing. They are the harbingers of the cold. As a shadow passes over a sensor, the temperature reading plummets in real time. From 400 degrees Celsius to 0 degrees Celsius in a matter of hours. This region of extreme temperature difference is called the terminator. On Earth, it's a gentle, diffuse zone. On Mercury, it's a razor's edge. An observer could have one foot in blistering heat and the other, a meter away in shadow, in a deep freeze of -100 degrees Celsius. The light during this long sunset is beautiful in a stark, alien way. With the sun low on the horizon, every crater rim and every grain of dust casts a long, sharp, black shadow. The landscape becomes a high-contrast etching. There are no colors of a terrestrial sunset, because there is no air to scatter the light. There is only the raw, geometric purity of light and its absolute absence. By day 110, the sun is a sliver on the horizon. The landscape is a world of long, spidery shadows. In the illuminated areas, the temperature is still over 100 degrees Celsius, but in the shadows, it is already -150 degrees Celsius. Standing on a ridge, an observer would watch the last brilliant point of light vanish. The universe would seem to snap. It is not a fade to black, it is like a switch being thrown. The last of the light is gone, and the darkness is total. The temperature, free from the sun's energy, begins its final, terrifying plunge toward the cryogenic abyss. The deep night. The night does not fall. It consumes. Within hours, the surface is at -170 degrees Celsius, heading back towards the -180 degrees Celsius that greeted the start of the day. The nearly 600 degrees Celsius temperature swing, from noon to midnight, is the most extreme of any planet in our solar system. The world becomes a tiny, fragile bubble of warmth in an infinite, deadly cold. The fear of being cooked is replaced by the equally constant reality of the freeze. But the night has its own terrifying beauty. With no sun, the stars are magnificent, a diamond dust scattered across perfect black velvet. But they are a cold fire, emphasizing the profound, abyssal cold. Life settles into a new, monotonous rhythm. The 88 Earth days of night stretch on. To combat the psychological strain of the eternal darkness, a strict schedule of 24-hour Earth cycles would be necessary, time for work, for recreation, for sleep. Sometimes, the only thing to do would be to watch the stars. Because of Mercury's slow rotation and short year, the celestial sphere wheels by at a strange pace. A constellation rises, transits the entire sky, and sets, all in the course of a few Earth days. It is a silent, grand, cosmic clock. The surface outside is a ghost. In the faint starlight, One could just make out the outlines of the craters and the long, wrinkled scarps. Scientists have long theorized that water ice might exist in the permanently shadowed craters near the poles. Here, in the temporary darkness of the equatorial night, one might wonder what strange chemistry is happening, as simple molecules freeze into a delicate frost on the supercooled ground. It is a tantalizing mystery in the long, dark hours. Days turn into weeks. Day 150, day 160, day 170, and then, a sensor on the eastern horizon would register a change. A tiny, almost imperceptible rise in energy. It is the first hint of the sun's corona, preparing to break the horizon once again. A new day is coming. A new 176 Earth day cycle of fire and ice is about to begin. For an observer, it is simply the turning of the wheel. The start of another lap in this impossible, beautiful marathon. The universe is full of extremes, but Mercury teaches a unique lesson about existence. It is a planet that reveals the true meaning of contrast and the profound influence of orbital mechanics. What we can learn there will stay with us. The sun that moves backward, the noon that melts lead, the night that freezes time itself, and the silence, the unending, absolute silence. Every planet holds its own secrets. Exploring these questions is why we study the cosmos, why we push the boundaries of what is possible to understand. Mercury is a world that appears hostile, yet in its hostility, it reveals the fundamental forces that shape planets. It is a reminder that what seems normal now is only a small, surviving slice of what is possible. The universe is waiting to be understood. We just have to be willing to look. Surviving Mercury's 176-day sunlight nightmare. There are places in our solar system that quietly challenge our idea of time. Imagine a world where a single period of sunlight lasts not for hours but for months. For 176 Earth days, the sun does not set. It hangs in the sky, a constant, unfamiliar presence, 3 times larger than you have ever seen it. This is not a thought experiment. It is the reality of Mercury. And for any human presence there, it would pose a fundamental problem. This isn't a story about the dramatic heat that can melt lead, or the cryogenic cold of the night. It is a story about something more subtle, light. An endless, unblinking stream of it. On Mercury, the very rhythm of day and night, a cycle our bodies are built around, is broken. A single solar day, from one sunrise to the next, stretches for an almost unbelievable 176 Earth days. So, how could we exist there? How could humanity carve out a place when our biology, our psychology, is so deeply tied to a 24-hour clock? Today, we are going to explore this question. We will look at the unusual orbital mechanics that create this environment, the quiet crises it would cause for a human mind, and then, the engineering solutions that might make survival possible. Because living on Mercury is not just about building a shelter from the elements. It's about shielding the mind from a day that never seems to end. The scientific breakdown, a planet where a day is longer than a year. Before we can design a survival strategy, we have to understand the quiet and unfamiliar nature of time on Mercury. It's a planet that follows rules different from our own. The numbers themselves help to frame the problem. Mercury rotates on its axis, what is called a sidereal day, once every 58.65 Earth days. Now, compare that to its year. It moves around the Sun in a fast 88 Earth days. Already, something feels different. A year on Mercury is only about 1.5 of its own rotations. But that is not the number that would define the lives of its colonists. The number that matters, the one that shapes their reality, is the solar day, the time from one sunrise to the next. On Mercury, that period is 176 Earth days long. A single day on Mercury is twice as long as a Mercury year. You would celebrate 2 full orbits around the Sun in the time it takes to go from one dawn to the next. What does this mean in practice? Imagine landing at sunrise. You would experience 88 straight Earth days of continuous sunlight. The sun would slowly, almost imperceptibly, crawl across the sky, reaching its peak after 44 Earth days. Then, it would take another 44 Earth days to finally set. Once it does, you are left in an equally long night, 88 Earth days of absolute darkness and deep cold. The question is, why? Why does this planet have such an unusual relationship with its star? The answer is found in a state of gravitational equilibrium called 3:2 spin-orbit resonance. Over billions of years, the immense gravity of the Sun has slowed Mercury's rotation until it settled into this stable, repeating pattern. For every 2 times Mercury orbits the Sun, it rotates on its axis exactly 3 times. Think of it like a gear system, with the orbit and the spin locked together in a precise ratio. This intricate dance is what stretches the solar day to such an extreme length. But the planet's behavior has other subtleties. Mercury's orbit is not a perfect circle, it's highly elliptical. This means its distance from the Sun changes, from about 46 million kilometers at its closest point, perihelion, to 70 million at its farthest, aphelion. Because of this, Mercury moves fastest in its orbit when it is closest to the Sun. For an observer on the surface, this change in speed creates a curious spectacle. Around the time Mercury is at its closest and fastest, its orbital speed can briefly overtake its rotational speed. The effect is that the Sun appears to stop in the sky, move backward for a short time, and then continue its westward journey. From certain longitudes, you could even witness a double sunrise. The Sun would rise above the horizon, dip back below it, and then rise again for the long day ahead. Imagine the psychological effect of that. The very anchor of our timekeeping, the Sun, behaving in such an unfamiliar way. This is not just an astronomical curiosity. This is the environment to be endured. When Mercury is closest to the Sun, the star appears about 2.5 times larger in the sky than it does from Earth, and the intensity of the sunlight is over 10 times greater. The 176-day cycle is the metronome of this world, counting out a rhythm of extreme heat, extreme cold, and a psychological pressure unlike anything a human has faced. Understanding this celestial clockwork is the first step, because every part of survival will be a response to this inescapable reality. The Cascade of Crises, Part 1, The Psychological Toll. Now, let's place ourselves in the habitat of a colonist. You have arrived. You are shielded from the vacuum and the radiation. But you cannot be shielded from the light. The Sun has risen, and it will remain in the sky for nearly 3 months. This is where the true challenge begins, not with a sudden failure, but with a quiet, creeping disruption of the human mind. Our bodies are finely tuned instruments, calibrated over millions of years to the 24-hour rhythm of Earth. This internal clock, our circadian rhythm, governs everything from our sleep-wake cycles to our mood and hormone release. It takes its primary cues from the rising and setting of the Sun. On Mercury, that cue is broken. The first and most immediate effect would be a profound disruption of sleep. In the presence of light, our brains suppress the production of melatonin, the hormone that signals it's time to rest. In an environment of 88 straight days of daylight, your body would be in a constant state of daytime, fighting the urge to sleep at every turn. Even with enforced night cycles inside the habitat, the biological confusion would remain. Research from polar expeditions on Earth, where crews face months of constant daylight, has documented severe consequences. Insomnia becomes common, sleep quality declines, people feel perpetually jet-lagged, a state of mental fog and exhaustion that never quite lifts. A minor 1-hour shift for daylight saving time can reduce sleep by 40 minutes on average. Now imagine the disruption of a 2,100-hour day. A colonist would feel a deep weariness, a constant struggle between the clock on the wall and their own biology. This lack of restorative sleep is a gateway to more serious psychological problems. The same light that affects melatonin also influences serotonin, a neurotransmitter important for regulating mood. Constant exposure could throw this delicate system out of balance. The closest comparison we have is seasonal affective disorder, or SAD, but the Mercury experience would be a different kind of beast. Studies have shown that increased light exposure can trigger manic episodes in some individuals. On Mercury, colonists could be living in a state of extended agitation for 3 months straight. Irritability could skyrocket. Minor disagreements could escalate into major conflicts. People would be emotionally raw, their patience worn thin. Then there is the subtle warping of one's perception of time. Without the daily rhythm of sunrise and sunset, the days would begin to blur into one another. The habitat's clocks would tick away, but they would feel arbitrary, a fiction superimposed on the reality outside. Psychological support would become as critical as any life support system. It would not be a luxury, it would be essential. Rigorously enforced schedules would be necessary, with artificial lighting designed to perfectly mimic an Earth day. These systems would shift color temperature from the blue-white light of morning to the warm, red-hued tones of evening, to try and coax the brain into producing melatonin. Virtual reality might become a form of therapy, allowing colonists to watch a simulated sunset just to give their minds the cues they crave. But even with all this, some may not cope. The constant glare could trigger visual disturbances, a phenomenon known as the Ganzfeld effect, where the brain, starved of new stimuli, begins to create its own. The psychological profile for a Mercury colonist would have to be incredibly robust. Even the strongest minds would be tested. The first casualties on Mercury might not be from a suit breach or a habitat leak, but from a quiet, internal collapse of the human psyche. The Cascade of Crises, Part 2, Physiological and Technological Impact. While a psychological battle would be fought in the minds of the colonists, an equally persistent one would be waged against their bodies and their technology. The same endless sun that fractures the circadian rhythm also unleashes a torrent of energy that breaks down matter. Let's start with the physiological impact. The disruption of the sleep-wake cycle has been linked to a higher risk of metabolic issues, cardiovascular problems, and a weakened immune system. On Earth, night shift workers show a significant increase in these problems over time. For Mercury colonists, this would be their permanent reality. The constant light and hormonal dysregulation could lead to chronic stress. Cortisol, the stress hormone, could fall into a chaotic pattern, leading to a range of negative health outcomes. Colonists might find their bodies physically deteriorating under the strain. The environment itself is, of course, exceptionally hostile. Daytime surface temperatures on Mercury can reach 427 degrees Celsius, or 800 degrees Fahrenheit, hot enough to melt lead. Any colonist outside would need a spacesuit far more advanced than anything we currently possess. A failure in a suit's cooling unit would have a fatal outcome within minutes. And then there is the radiation. Mercury has only a thin exosphere, offering almost no protection from the sun's high-energy particles. Its magnetic field is also very weak. Any surface structure would need to be heavily shielded, likely buried under several meters of regolith, the planet's loose soil. Underground habitats would be a necessity, not a choice. This brings us to the technological crisis. The success of any colony depends on the reliability of its machines. On Mercury, every piece of surface equipment is in a constant battle for survival. Solar panels would be incredibly effective during the long day, but the extreme heat would accelerate their degradation. Then, during the 88-day night, temperatures would drop to a cryogenic -173 degrees Celsius, -280 degrees Fahrenheit. This massive temperature swing would cause materials to expand and contract violently. This thermal cycling is damaging to complex electronics, causing solder joints to crack and components to fail. Imagine a critical rover or maintenance bot. For 88 days, its parts are baked. Its lubricants could vaporize. Then, for the next 88 days, it freezes. Seals could fail, and plastics could become brittle. The colony would be in a constant state of repair. Power management would also be a profound challenge. The colony needs electricity all the time, but its primary power source is only available half the time. This requires a massive energy storage solution. During the long day, solar arrays would have to generate enough power to run the colony and charge a system capable of lasting through the entire 88-day night. The scale of such a facility would be immense. The series of challenges is clear. A tired and stressed population is tasked with maintaining advanced, failure-prone technology in an environment that is actively trying to destroy it. This is the narrow path the colonists must walk. A constant struggle against the decay of their own minds, their own bodies, and the machines that keep them alive. The Quest for a Solution. Part 1. Location, location, location. So, how does one approach these challenges? How do you build a home on a planet that seems so determined to be uninhabitable? The answer, as it is in real estate, begins with location. If you cannot endure the endless day, you must find a place where the sun never shines. On Mercury, such places exist. The key is Mercury's axial tilt. The planet spins almost perfectly upright, with a tilt of just 2 degrees. This means the sun is always directly over the equator. As a result, at the planet's poles, there are deep impact craters whose floors have not seen direct sunlight for billions of years. These are craters of permanent shadow. Inside these craters, one finds the inverse of Mercury's sun-baked equator, a stable, predictable, and cold environment. And in that cold, you may find the single most precious resource in the solar system, water ice. For decades, scientists suspected these regions could act as cold traps. In 1991, radio telescopes detected bright, radar-reflective patches at Mercury's poles, a tantalizing hint. The confirmation came from NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Its neutron spectrometer detected large amounts of hydrogen, the primary component of water, in these permanently shadowed regions. The data strongly suggests the presence of water ice, though its exact abundance is still a subject of study. This discovery is a game-changer for colonization. These polar craters offer a solution to several of Mercury's deadliest problems in one package. First, they solve the sunlight problem. By building a habitat on a crater floor, colonists would be permanently shielded from the sun. The 176-day solar cycle becomes irrelevant. The colony could operate on a strict 24-hour Earth clock, with artificial lighting providing a simulated dawn and dusk. The psychological pressure of the endless day would be lifted. Second, the craters provide a solution to the extreme temperatures. The temperature on the floor of a permanently shadowed crater is incredibly stable, hovering around -173 degrees Celsius, -280 degrees Fahrenheit. While this presents its own engineering challenges, it is a far easier problem to solve than surviving the heat. It is always easier to generate heat than it is to get rid of it in a vacuum. The stable temperature also eliminates the destructive thermal cycling. Third, and most critically, the presence of water ice is the key to self-sufficiency. Water is life. It can be purified for drinking, used for growing crops, and split into hydrogen and oxygen. Oxygen provides breathable air. Hydrogen and oxygen are powerful rocket fuel. A polar colony on Mercury could, in theory, mine ice to create its own air, water, and fuel. The architecture of such a base would be fascinating. To solve the power problem, colonists could place solar arrays on the crater rim, on what are known as peaks of eternal light. These are points high enough to be in near continuous sunlight. Power cables would run from these solar farms down to the base, providing an uninterrupted supply of electricity. Life in a polar crater would be a unique existence, while life lived in a contained, artificially lit world. The great, terrible sun would be reduced to a concept, a source of power from over the horizon, but never a direct threat. This solution, hiding in the shadows, trades the dynamic environment of the equator for a cold, stable, and ultimately, more survivable home. The quest for a solution. Part 2. The Terminator line. Hiding in a dark, frozen crater is a static, stable solution. But it is not the only one. What if, instead of hiding from the sun, you could keep pace with it? What if a habitat could be built to be constantly in motion, forever chasing the sunset? This is a second, more dynamic idea. Living on Mercury's Terminator line. The Terminator is the division between the day side and the night side of a planet. It is the zone of perpetual twilight. On Earth, this line sweeps across the surface at over 1,600 kilometers per hour. But Mercury is different. Because of its incredibly slow rotation, the Terminator line crawls across the surface at little more than a walking pace. At the equator, the surface is moving at only about 10 kilometers per hour, around 6 miles per hour. This opens up a fascinating possibility, a mobile colony. Imagine a habitat, not on a fixed foundation, but on massive tracks or wheels. This city would roll across the Mercurian landscape, keeping pace with the planet's slow rotation. Its mission? To stay permanently within the narrow band of twilight. Life in such a moving city would be unusual. The sun would be a permanent fixture on the horizon. Depending on which side of the Terminator you were on, it would be either perpetually rising or perpetually setting. You could live your life in the gentle, angled light of a never-ending golden hour. This strategy ingeniously solves the temperature problem. Instead of dealing with the extremes, the Terminator offers a more manageable environment, where the ground is neither scorching nor frozen. It also presents a unique solution to the power problem. The city would be flanked by solar panels angled toward the low sun, constantly generating power. There would be no need for the massive energy storage systems of a static base. However, the engineering challenges are considerable. First, you need a city-sized vehicle that can reliably travel across a cratered, unmapped surface for centuries without fail. A single, catastrophic breakdown would be critical. If the city stops, the Terminator line keeps moving, and the habitat would be slowly engulfed by either killing heat or freezing cold. Navigation would be a constant, high-stakes task. The city would need advanced radar and mapping to avoid treacherous terrain. And what about resources? A polar base sits on its water ice. A rolling city would need to be a mobile mining operation as well, stopping to gather materials. Perhaps the solution is a hybrid one, a main polar base with smaller, Terminator roving outposts. Psychologically, life on the Terminator would be different. The landscape would be forever changing, but the sky would be eerily constant. Colonists would still be entirely dependent on artificial clocks and lighting cycles to regulate their lives. The idea of a city moving with the twilight is a compelling one. It speaks to a nomadic form of existence. It is a vision of humanity not hiding from the environment, but moving with it, in time with the slow, deliberate rhythm of an alien world. So, we are faced with two paths on the surface of Mercury. We have been confronted with a problem of perpetual light, a 176-day cycle that threatens the human mind and our technology. But we have also found hope in the shadows and in motion. The first path is to settle in the permanently shadowed craters of the poles. There, we can escape the sun, find stable temperatures, and access reservoirs of water ice. This is the safe, static, and perhaps most realistic option. The second path is that of the nomad. A city on wheels, forever chasing the twilight. This solution embraces the planet's strange rotation, turning it into an advantage. It offers moderate temperatures and continuous power, but at the cost of immense mechanical complexity. In the end, colonizing Mercury would be one of the greatest challenges humanity could undertake. The sheer hostility of the environment, dominated by that long, brutal solar day, demands a new level of resilience. The colonists of Mercury would be a different breed of pioneer, living lives dictated by the clock, not the sky, in worlds of either perpetual shadow or perpetual sunset. Their survival would be a powerful statement about the tenacity of life and human ingenuity. But it also serves as a quiet reminder of how precious and finely tuned our own world is. The next time you watch a sunset and feel the gentle transition from day to night, take a moment to appreciate that simple, 24-hour rhythm. It is a gift, one that the survivors on Mercury would dream of every single day. If you had to choose, which path would you take? The quiet safety of a polar crater, or the endless journey along the Terminator line? Let me know your thoughts in the comments below. What Mercury teaches us about the illusion of time. There is a rhythm we all feel. A quiet, steady beat that seems to hold the world together. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. It feels absolute, a fundamental piece of reality itself. We wake, we work, and we sleep, all moving to this shared pulse. Our lives, our biology, our entire world is built on the simple, reliable turning of the Earth. But what if that rhythm, as fundamental as it feels, is only local? What if just next door, in our own solar system, a world exists that moves to a different beat entirely? A world where a single day lasts longer than 2 of its years. This is not a story from science fiction. This is the planet Mercury. Its strange, almost unbelievable sense of time is not just a planetary curiosity. It is a quiet clue, leading us toward a deeper secret about the universe. That time, as we experience it, might be an illusion. And understanding that illusion doesn't just change how we see a distant planet, it quietly changes how we understand reality itself. Imagine a world where you could watch 2 of your birthdays pass in a single day. Not 2 birthdays in a 24-hour period, but 2 full journeys around the sun completing before you've seen a single sunrise and sunset. On Mercury, a year, the time it takes to circle the sun, is a brief 88 Earth days. But a solar day, the time from one noon to the next, stretches for 176 Earth days. A day is twice as long as a year. This is not just a piece of trivia. It challenges our deepest feelings about how time works. How can a day and a year be so disconnected? How can a planet spin so slowly while its path around the sun is so quick? The answer is found not in a cosmic mistake, but in a strange and quiet dance between gravity and motion. It is a dance that would eventually lead us to rewrite our understanding of the universe and of time itself. To understand this, we first have to look away from the sky and turn our attention inward, to the assumptions we hold so closely right here on Earth. For every human who has ever lived, the day has been the first and most fundamental measure of time. Long before clocks or calendars, there was the sun. Its rising and setting created the first great rhythm of life. It's a rhythm so deep inside of us, it seems to be written into our biology. Our bodies follow circadian rhythms, an internal, 24-hour clock that tells us when to feel awake and when to feel tired, all tuned to the light of the sun. Our societies are built around it. Our work, our rest, our global economies all move to the beat of this 24-hour pulse. This familiar rhythm is the product of a simple piece of planetary mechanics, the rotation of the Earth on its axis. As our world spins, different parts of its surface turn to face the sun, creating the cycle of day and night. It feels so natural, so correct, that we have projected this idea onto the entire universe. When we think of a day on another planet, our minds tend to imagine a similar cycle, maybe shorter, maybe longer, but fundamentally the same. We take our local experience and assume it is a universal model. For centuries, the way we kept time was a direct reflection of this solar cycle. Ancient Egyptians used obelisks as giant sundials, watching the movement of a shadow to divide the daylight hours. Water clocks were created to measure time at night, but they were always set against the final authority of the sun. Even as mechanical clocks grew more sophisticated, their purpose was to copy and standardize the solar day, to break it down into smaller, even pieces. The clock did not invent time, it only echoed the time that the Earth and Sun provided. This history has given us a deep and quiet bias. We see time as a constant, external thing, like a river that flows at the same speed for everyone, everywhere. Isaac Newton, one of the founders of classical physics, gave this idea a formal name. He described absolute, true, and mathematical time, which, he believed, from its own nature, flows equably without relation to anything external. For Newton, a second on Earth was a second on Mercury and a second on the most distant star. It was the ultimate constant, the unwavering background for all of motion. The idea is powerful and intuitive. And for most of history, it worked perfectly. It allowed us to navigate oceans, build cities, and create the foundations of industry. The universe, in Newton's view, was a giant, predictable clockwork machine, and time was the single key that wound it. But this elegant picture of the universe had a small, persistent problem. An anomaly hiding in our own celestial neighborhood. A problem with the orbit of the planet closest to the Sun. A problem that Newtonian physics could not seem to solve. This small inconsistency would eventually change the entire concept of absolute time, and it all began with Mercury. The planet seemed to be following a different set of rules, and to understand them, we must first appreciate just how unfamiliar its rules are. To truly understand what Mercury shows us, we have to travel there, not in a ship, but in our imagination. Forget Earth's gentle 24-hour waltz. Mercury is in a different kind of dance with the sun, one that moves in a way that defies our terrestrial expectations. The heart of the paradox is in two numbers, 88 and 176. It takes Mercury just 88 Earth days to make one full orbit around the Sun. This is its year, but the experience of a day on Mercury is something else entirely. A solar day, from one sunrise to the next, lasts for 176 Earth days. A single day is twice as long as an entire year. You would experience a full journey around the Sun, and the Sun would have only made it halfway across your sky. You would celebrate your first birthday, and then, 88 days later, your second birthday, all before seeing a single sunset. This reversal of what we consider normal is the first clue that something is fundamentally different about Mercury. The reason for this temporal strangeness is a phenomenon called spin-orbit resonance. It sounds complex, but it is really just a description of a quiet gravitational relationship. For a long time, astronomers believed Mercury was in a 1-to-1 resonance, meaning it rotated once for every one orbit, always keeping the same face toward the Sun, just as our Moon does with Earth. They were wrong. In 1965, radar observations revealed the truth. Mercury is in a 3-to-2 spin-orbit resonance. It rotates on its axis exactly 3 times for every 2 orbits it completes around the Sun. Imagine it as a set of celestial gears. For every 2 turns of the gear, the day gear turns 3 times. This specific, stable ratio is the result of the Sun's immense gravity acting on Mercury's slightly elliptical, or egg-shaped, orbit. This 3-to-2 relationship is what creates the 176-day solar day. Let's walk through it. Imagine standing on Mercury as the Sun appears on the horizon. Your long day begins. After 58.6 Earth days, Mercury has rotated once on its axis. But in that same time, it has also traveled 2/3 of the way around the Sun. So the Sun is not back where it started in your sky, it's still high overhead. It takes 3 full rotations of the planet, and 2 full orbits around the Sun, for the Sun to finally return to the same spot in your sky. But the paradox becomes stranger still. This is not a smooth, steady journey of the Sun across the sky. Because Mercury's orbit is so eccentric, its speed changes. It moves fastest when it is closest to the Sun and slowest when it is farthest away. At certain times, when it is closest to the Sun, Mercury is orbiting so fast that its movement around the Sun outpaces its rotation on its axis. From the surface, this would look like a subtle, almost dreamlike event. You would see the Sun rise and climb into the sky, but then, as Mercury speeds up, the Sun would appear to stop, move backward for a short while, stop again, and then continue its slow journey forward. This retrograde motion of the Sun is a real, observable phenomenon on Mercury. The same thing happens in reverse at sunset. This strange reality, a day twice a year, a Sun that moves backward, was not just a curiosity. It was a symptom of a deeper problem, one that had puzzled astronomers for more than half a century. The precise nature of Mercury's orbit, the very dance that creates this unfamiliar sense of time, did not add up. It was a quiet rogue, refusing to obey the laws laid down by Isaac Newton. By the middle of the 19th century, Newtonian physics was seen as a pillar of certainty. Its laws of motion and gravity could predict the path of a planet with incredible precision. In 1846, this belief had its greatest moment. Astronomers noticed that the planet Uranus was drifting slightly from its predicted path. Instead of questioning the laws, the mathematician Urbain Le Verrier suggested there must be an unseen planet pulling on Uranus. He trusted Newton's laws, calculated the position of this phantom world, and sent his prediction to the Berlin Observatory. On the very first night they looked, astronomers found the planet Neptune, exactly where Le Verrier said it would be. It was a profound triumph. So, when Le Verrier turned to another, much smaller problem, the world expected a similar resolution. The problem was Mercury. Like Uranus, Mercury's orbit was not behaving. All planetary orbits slowly rotate, or precess, over time, pulled by the gravity of the other planets. Le Verrier calculated the expected precession of Mercury's orbit based on all the known planets. But there was a mismatch. The actual orbit was precessing slightly faster than the laws predicted. The difference was minuscule, just 43 arcseconds per century. An arcsecond is 1/3600th of a degree. It was an impossibly small number that held an enormous question. It was a quiet crack in the seemingly perfect structure of Newtonian physics. For Le Verrier, there was only one plausible explanation, the one that had worked so well before. He proposed the existence of another planet, or maybe a belt of asteroids, orbiting even closer to the Sun. He gave this hypothetical planet a name, Vulcan. The hunt began. In 1859, an amateur astronomer named Edmond Lescarbault claimed to have seen a small dot cross the face of the Sun, believing it to be the new planet. Le Verrier, convinced, announced the discovery to the world. For decades, astronomers searched for Vulcan. There were more claimed sightings, but none were ever confirmed. The phantom planet remained a ghost, an idea created to save the laws of Newton. The problem persisted for more than 50 years. The answer, it turned out, was not to add another piece to the puzzle. The answer was to change the shape of the puzzle itself. To solve the riddle of Mercury, science needed someone to not just add a new planet, but to fundamentally reimagine space, gravity, and time. That person was a young patent clerk in Switzerland named Albert Einstein. In 1915, after a decade of intense intellectual work, Albert Einstein presented his general theory of relativity. It completely replaced the Newtonian picture of gravity. For Newton, gravity was a force, an invisible pull between objects. Einstein proposed something far more profound. He said that gravity is not a force at all. It is the consequence of mass and energy bending the very fabric of the universe, a four-dimensional fabric he called space-time. The usual way to picture this is to imagine a trampoline. A bowling ball placed on the trampoline creates a deep curve in the fabric. If you then roll a small marble nearby, it doesn't fall toward the bowling ball because of a mysterious force. It simply follows the curve in the surface created by the bowling ball. This is what Einstein said gravity is. Massive objects like the Sun don't pull on the Earth. They warp the spacetime around them, and the Earth, in its orbit, is simply following the straightest possible path through that curved spacetime. What we feel as gravity is just the sensation of moving through a universe that is not flat. But this is where the idea becomes something more. Einstein realized it wasn't just space that was curved. It was time, too. The two were woven together. Where gravity is stronger, where spacetime is more curved, time itself passes more slowly. This is not a metaphor. It literally is slower. This effect is called gravitational time dilation. A clock at sea level will tick slightly slower than a clock on a mountain. This is a real, measurable effect. The satellites that make up the Global Positioning System, GPS, are in a weaker gravitational field than we are on the surface, so their clocks tick slightly faster. If scientists did not correct for this relativistic effect, GPS navigation would fail within a single day. This was a quiet revision of Newton's idea of absolute time. There is no single, universal clock. Time is relative. Its pace depends on your motion and the strength of the gravity you are in. Every planet, every star, has its own local time. Your personal experience of time is unique to you. With this new framework, Einstein turned to the 50-year-old problem of Mercury's orbit. He suspected the answer was not a phantom planet, but the curvature of spacetime itself. This would be the first real-world test of his incredible new vision of the cosmos. In November of 1915, Albert Einstein applied the equations of general relativity to the orbit of Mercury. He wasn't trying to force an answer. He was simply following the rules of his new understanding of the universe to calculate how a planet should move through the curved spacetime created by the Sun. The Sun, as the most massive object in our solar system, creates the deepest gravity well. As Mercury orbits, it doesn't just travel on a simple ellipse. It travels on an ellipse that is itself being dragged around by the curvature of space. When Mercury swings closest to the Sun, it dips deeper into this gravity well, where spacetime is more severely curved. Its path is altered more than Newtonian physics would predict. This additional shift, this extra bit of precession, was what Einstein calculated. The result was astonishing. The numbers on his page revealed a prediction for an anomalous precession of 43 arcseconds per century. It was the exact amount that had been observed. There was no need for a phantom planet Vulcan. The discrepancy was explained perfectly by the fact that Mercury was orbiting through a universe where space and time were not absolute. Einstein himself was, as he wrote to a friend, beside myself with joy. He knew this was the first profound confirmation of his theory. The universe really did work this way. Mercury's strange orbit was no longer a problem. It was the first hard evidence for a completely new understanding of reality. And this brings us back to Mercury's strange day. The same forces that explain the precession of its orbit also help us understand its slow rotation. The 3-to-2 spin-orbit resonance is a stable state it settled into, a direct consequence of the powerful tidal forces from the Sun. The planet is caught in a gravitational relationship so tight that it dictates this strange, slow day relative to its year. So Mercury's slow rotation, its day that lasts for 2 of its years, its sun that moves backward in the sky. All of these are symptoms of living deep inside a star's gravity well, where the rules of time and space are bent. It is a living laboratory for relativity, a reminder that our Earth-based sense of time is just that, a local bias. The lesson from Mercury's orbit is not confined to that one small world. The realization that gravity warps time has rippled out to touch all of modern physics. It is a universal principle, and once you know to look for it, you begin to see its effects everywhere. It is at work in the GPS in your phone, which must account for the fact that time moves at a different rate for the satellites in orbit than it does for us on the ground. There is no single, shared, now, between you and the satellite. Now, if we follow this idea to its most extreme conclusion, we arrive at one of the most mysterious objects in the universe: a black hole. A black hole is a region of space-time where gravity is so intense that nothing can escape. It is the ultimate warping of space-time. Near a black hole, the effects of gravitational time dilation become extreme. If you could hover just outside its event horizon, you would see a distant clock on Earth ticking incredibly fast. Millennia on Earth could pass in just a few of your hours. An observer on Earth watching you would see your clock ticking almost infinitely slowly. You would appear to be frozen in a single moment. From the subtle wobble in Mercury's orbit to the physics of a black hole, the lesson is the same: time is not a rigid, universal metronome. It is a flexible dimension, woven together with space. Our perception of a steady, 24-hour day is a product of our specific place in the cosmos. Mercury, in its eccentric and temporally strange dance, is the ultimate corrective to our cosmic expectations. It breaks the illusion and forces us to confront the much stranger reality that lies beneath. We began with a simple, familiar concept: the 24-hour day. A rhythm so fundamental it feels like a law of nature. But this law is merely a local one. Mercury, with its years shorter than its day, is a quiet testament to this fact. For a long time, we saw its strange orbit as a problem to be solved, an error in the cosmic clockwork. We invented a phantom planet to patch the hole in our understanding. But the problem was never with Mercury. It was with our expectation that time must be the same everywhere. Einstein's revolution was to realize that the universe does not have a single master clock. It has countless local clocks, all ticking at different rates, all subject to the flow of gravity. The 43 arcsecond discrepancy in Mercury's orbit was not an error, it was a message. It was the universe telling us that time is flexible, space is curved, and the two are bound together. Mercury teaches us that our experience of reality is shaped by our environment. Our sense of time is a consequence of Earth's mass, its spin, and its distance from the Sun. It is not universal. By studying this small, sun-blasted world, we learn that the steady ticking of a clock is not the sound of an absolute, cosmic metronome. It is the sound of our own world, spinning in its own unique way, in its own quiet corner of a vast and relativistic universe. If this kind of calm exploration into the nature of time helps you see the universe in a new way, consider liking the video and subscribing to the channel. And wherever you are right now, whether it's day or night, feel free to share in the comments what other cosmic mystery or paradox you feel drawn to.